Hello there, and welcome back. I'm so glad you decided to spend a little time here tonight, settling in under the soft weight of your blankets while the world outside grows quiet. Whether you're lying in bed with the lights dimmed, or perhaps resting on the couch with the gentle glow of your screen casting shadows on the ceiling, I hope you found a comfortable spot. This is your time now. The day has done what it was going to do, and there's nothing left that needs your attention. At least, not until tomorrow. Before we begin our gentle wandering through the cosmos this evening, I wanted to ask you something. How was your day? I know I can't hear your answer, not in the usual way, but I find myself genuinely curious about the small and large moments that filled your hours before you arrived here. Maybe it was one of those days that felt impossibly long, where every task seemed to require more energy than you had to give. Or perhaps it was quieter than that. A Tuesday that simply passed, unremarkable but steady, like breathing. Maybe something made you laugh today, or someone said something kind, or you noticed the way the light fell through a window in a way you hadn't before. Whatever your day held, I'd love for you to share it in the comments below. Even just a word or two. It's a small thing, but there's something lovely about leaving a little piece of your day in a place where others might find it, where someone scrolling through at 3 a.m. might read your words and feel a little less alone in their own quiet moment. And while you're there, if you haven't already, I'd be grateful if you'd consider subscribing to the channel. It's such a simple gesture, just a click, but it means the world to me. It helps these videos find their way to other restless minds, other tired hearts looking for a soft place to land at the end of their own long days. Plus, I have so many more journeys planned for us, through the depths of the ocean, into the hidden lives of stars, along the strange and beautiful pathways of the human mind. I'd hate for you to miss any of them, but enough of that. You didn't come here for housekeeping, did you? You came here to drift, to let your thoughts unspool and your body grow heavy, to learn a little something while sleep gathers at the edges of your consciousness, like fog rolling in from the sea. Tonight, we're going to talk about space, that vast, dark, magnificent expanse that stretches above us even now, even as you lie here with your eyes growing soft and your breathing beginning to slow. We'll explore the strange and wonderful facts that make the cosmos such an endlessly fascinating place, from the texture of interstellar emptiness to the ancient light of distant galaxies, from the smell that clings to spacesuits after a walk among the stars, to the profound mysteries that keep physicists awake at night, even as their contemplation might help you fall peacefully asleep. Now, let's begin. When we think about space, that great dark canvas stretched between the stars, we often imagine it as emptiness itself, the very definition of nothing. A vacuum, we call it. And the word sounds so hollow, so absolute. But here is a gentle truth to carry with you into sleep tonight. Space isn't completely empty. Even in the vast reaches between galaxies, where light must travel for millions of years without encountering anything of substance, there exists something. About 1 atom per cubic centimeter, on average, drifting through the darkness like the most solitary travelers imaginable. 1 atom per cubic centimeter, It sounds like almost nothing, and in a sense, it is. The air you're breathing right now contains roughly 25 quintillion molecules in that same space, a number so large it loses all meaning when you try to hold it in your mind. In comparison, one atom seems like loneliness made physical, like a single voice calling out across an ocean with no shore in sight. And yet, it's there, the universe, even in its most remote and seemingly barren regions, is not quite empty. It's just very, very quiet. What makes this even more remarkable is that this makes space a better vacuum than anything we've ever managed to create here on Earth. In our most sophisticated laboratories, using our most advanced technology, we cannot produce emptiness as pure as what exists naturally between the stars. We try and try, pumping away at chambers and cooling them to incredible temperatures. And still, we cannot match what the cosmos has achieved simply by being vast. There's something humbling in that, don't you think? All our cleverness and machinery, and we cannot replicate the simplest thing the universe does without effort. Perhaps there's comfort in knowing that true emptiness doesn't exist, that wherever you might travel in this infinite expanse, you would never be completely alone. Even in the coldest, darkest corner of creation, there would be something there with you, a hydrogen atom, perhaps, or a stray helium nucleus, keeping you company in its own quiet way. The universe, it seems, is subtly full of invisible presence, like a room that feels inhabited even when you can't see anyone there. And as you lie here in the soft darkness of your own room, maybe that thought can settle over you like a blanket. You are never truly alone. The emptiness is only apparent. Everything, everywhere, has something in it, even if that something is almost nothing at all. Here is something you might not have expected to learn as you drift towards sleep. Space has a smell. The astronauts who have walked beyond the bounds of our atmosphere, who have floated in the darkness with nothing but a suit between them and eternity, have come back with the same curious report. When they return from their spacewalks, when the airlock repressurizes and they remove their helmets, a distinctive scent clings to their equipment. They describe it as something like seared steak or hot metal or the sharp tang of welding fumes. An industrial smell, but also somehow organic. The smell of cooking and creation mingled together. Isn't that strange and wonderful to consider? We imagine space as sensory deprivation, silent, dark, and cold, and yet it leaves its mark on the things that pass through it. The astronauts' suits carry the cosmos home with them, perfumed by the void. Some have said the smell reminds them of gunpowder. That acrid bite that lingers after a firework has spent itself against the night sky. Others compare it to raspberries, of all things, because of certain compounds that float through interstellar clouds. The universe, it seems, has many fragrances. This scent comes from something called polycyclic aromatic hydrocarbons, complex carbon-based molecules created in the hearts of dying stars. When massive stars reach the end of their lives, when they've burned through their fuel and begun their long collapse, they scatter these molecules into space like seeds from a dandelion. They drift through the cosmos for millions of years, these tiny chemical messengers, carrying with them the essence of stellar death. And when astronauts venture outside their spacecraft, when they move through that thin boundary between our world and the infinite. These molecules cling to their suits and hitch a ride back inside. There's something poetic about that, isn't there? The smell of space is the smell of dying stars. Every time an astronaut catches that distinctive scent, they're experiencing a kind of cosmic perfume, distilled from the final moments of suns that burned out long before our own was born. It's as if the universe is leaving little notes for us, invisible messages written in chemistry and carried on the fabric of spacesuits. And tonight, as you breathe slowly and let your body grow heavy, maybe you can imagine that smell, metallic and strange and somehow alive, drifting through the darkness above your roof, waiting for someone to carry it down to earth. When you were young, perhaps you visited a beach. Perhaps you sat there in the sunshine, letting sand run through your fingers, marveling at how many individual grains there seemed to be. You might have tried to count them, the way children sometimes do with impossible things, before giving up and accepting that some numbers are simply too large to hold. But here is something to carry with you into your dreams tonight. There are more stars in the universe than grains of sand on all of Earth's beaches combined. Let that thought settle over you for a moment. Every beach you've ever walked along, every stretch of sand from the shores of Norway to the coasts of Australia, from the tiny hidden coves of the Mediterranean to the vast sweeping dunes of the Sahara that were once sea floor. Gather up every single grain from all of them, and you still would not have enough to match the number of stars burning in the cosmos right now. Scientists estimate there are around 200 billion trillion stars out there, a number so vast that writing it out would take 24 digits. 2 with 23 zeros after it, a number that exists only as an abstraction, a placeholder for the incomprehensible. And this number keeps growing as our telescopes improve, as we peer deeper into the darkness and discover that what we thought was empty is actually crowded with ancient light. Every advance in technology reveals more stars than we knew existed, more galaxies spiraling in the distance, more burning points of light that have been shining for billions of years without anyone to see them. The universe is not just large, it is extravagantly, almost wastefully full. It creates stars the way a summer meadow creates wildflowers, in numbers that seem designed to overwhelm, to make counting itself feel absurd. What do we do with a number like that? How do we fit it into our minds, which evolved to track the movements of perhaps 100 tribe members, to count the days until the next full moon, to estimate whether there were enough berries on a bush to make stopping worthwhile? We can't, really. The number of stars slides off our consciousness like water off glass. And maybe that's all right. Maybe the proper response to 200 billion trillion isn't understanding, but simply wonder. A soft exhale in the darkness, a gentle acknowledgement that we are part of something so much larger than ourselves that comparison becomes meaningless. As you drift towards sleep, perhaps you can let that vastness be a comfort rather than a vertigo. All those stars burning away in the silence, keeping the darkness company. The light falling on your pillow right now, if any still lingers from a lamp or a street light outside your window, reaches you almost instantly. It crosses your room in a fraction of a second. so quickly that for all practical purposes, it travels no time at all. But the light from our sun takes a journey before it arrives here. 8 minutes and 20 seconds, crossing 93 million miles of empty space to reach the Earth and warm your face on a summer afternoon. The sunlight you felt today was already old by the time it touched you. Think about what this means. When you look at the sun, though you shouldn't look directly, of course, not without protection, you're not seeing it as it exists in this moment. You're seeing it as it was 8 minutes and 20 seconds ago. In that time, someone might have made a cup of tea, or read a poem, or walked halfway to the corner store. The sun you see is always a sun of the past, a portrait of a moment that has already slipped away. We live, all of us, in a universe of delayed messages, where the present is something we can never quite catch. This delay becomes more pronounced the farther we look. The light from the nearest star system, Alpha Centauri, takes over 4 years to reach us. The light from the Andromeda Galaxy, our nearest large galactic neighbor, takes 2.5 million years. When you look at Andromeda in the night sky, and you can, with your naked eyes, on a clear, dark night, you're seeing light that began its journey when our ancestors were still learning to chip stones into tools. The galaxy you observe may have changed entirely since then. Stars may have been born and died, planets may have formed and crumbled to dust, and we would have no way of knowing. We're always looking at history, never at the present. There's something meditative in this, something that might help quiet the mind as sleep approaches. We cannot rush the cosmos. We cannot demand immediate answers from the stars. Everything comes to us in its own time, carried on beams of light that have traveled inconceivable distances to meet our eyes. The universe is patient, and perhaps it's teaching us to be patient too. The light will arrive when it arrives. The truth of distant places will reveal itself eventually. For now, we can only wait and watch and wonder at the ancient photons that fall so gently upon us from the depths of time. There is a world in our solar system where time moves in ways that seem backward, where the familiar rhythm of days and years gets tangled up and inverted. Venus, shrouded in thick clouds of sulfuric acid, rotates so slowly on its axis that one Venusian day, one complete rotation, takes longer than one Venusian year. A day on Venus lasts 243 Earth days, while its journey around the Sun takes only 225. The planet completes its orbit before it finishes a single sunrise to sunrise cycle. Let that thought settle into you like a stone sinking into still water. On Venus, you would experience more years than days. Birthdays would come and go while you waited for the afternoon to arrive. The concept of today would stretch across what we would call months. A single uninterrupted span of either light or darkness, depending on which face of the planet you stood upon. Time there would feel viscous, thick, like honey poured from a jar in slow motion. Everything we understand about the rhythm of existence would need to be reconsidered. And Venus rotates backward, too, compared to most other planets. If you could stand on its surface, which you couldn't, of course, because the pressure there would crush you and the temperature would melt lead, you would see the sun rise in the west and set in the east. Everything is reversed, inverted, contrary to expectation. Scientists believe this might be because of a massive collision early in the planet's history. Something so violent it not only slowed Venus's rotation, but reversed it entirely. A catastrophe so complete it rewrote the rules of day and night. Perhaps there's something almost restful in imagining such a place, where time moves so slowly that hurry becomes impossible. No rushing through your morning, no racing against the clock, just the long, slow crawl of shadows across a landscape so hot and pressurized that it feels like another universe entirely. Venus reminds us that our experience of time is not universal, that elsewhere in the cosmos, the beat of existence moves to entirely different rhythms. As you lie here in the darkness, breathing slowly, letting go of the day, maybe you can feel a little of that Venusian patience seeping into you. There is no rush. The day will turn when it turns. On the surface of the moon, preserved in gray powder that has never known wind or rain, there are footprints, human footprints. 12 people walked there between 1969 and 1972, pressing their boots into the fine lunar soil and leaving marks that will remain for millions of years. There is no weather on the moon to erode them, no wind to scatter the dust, no water to wash the impressions away. Those footprints are perhaps humanity's most enduring physical legacy beyond our own planet. Think of all the footprints you've left in your life, on beaches that the tide erased within hours, on snowy sidewalks that melted by noon, on muddy paths that dried and cracked and blew away. We leave marks everywhere we go, but almost all of them are temporary, fleeting impressions that the world smooths over as soon as we've passed. The earth is constantly remaking itself, constantly erasing our traces and preparing fresh surfaces for new stories. But the moon remembers. The moon keeps everything. Those astronaut boot prints, the familiar tread patterns pressed into alien soil, will outlast every building we have ever constructed, every road, every monument. They will persist through ice ages and the rise and fall of civilizations, through events we cannot possibly predict. Long after the pyramids have crumbled to sand, long after the great libraries and cathedrals have been forgotten, those quiet impressions will remain on the moon's surface, waiting for someone to find them, waiting to tell whatever future beings might arrive that once creatures from the blue planet nearby managed to cross the void and walk here. There is something both triumphant and melancholy in this thought. We reached out to touch another world, and the touch will last almost forever. And yet, no one has walked on the moon in over 50 years now. The footprints wait in silence, companions to no one, recording a burst of human ambition that flickered and then, for a while at least, went quiet. Perhaps someday will return, and new footprints will join the old ones. Perhaps the moon's surface will become crowded with our marks. But for now, those 12 sets of boot prints keep their lonely vigil, the most patient monuments we have ever made, preserving memories of afternoons spent in a place with no afternoons at all. In the cosmos, there exist objects of such impossible density that the mind struggles to comprehend them. Neutron stars are the collapsed cores of massive stars that have exploded in supernovae, crushed down by gravity into spheres perhaps 20 kilometers across. Just 20 kilometers. You could drive that distance in 15 minutes on a highway. And yet, a neutron star contains more mass than our sun, all of it compressed into that tiny space. A teaspoon of neutron star material would weigh about 1 billion tons. Let that number wash over you without trying to grasp it. 1 billion tons. Imagine every car in your city, every building, every ship in the harbor, every airplane that ever flew. Compress them all into a teaspoon, and you still wouldn't be close. The matter in a neutron star is packed so tightly that the electrons have been squeezed into the protons, creating neutrons that press against each other with almost no space between them. It is matter in its most extreme and desperate state, crushed down to the very limits of what physics allows before something even stranger, a black hole, forms instead. And yet, despite this unimaginable density, neutron stars are real. They spin through the cosmos, some of them rotating hundreds of times per second, their surfaces rippling with starquakes and magnetic fields trillions of times stronger than Earth's. They are objects that seem like they should exist only in mathematics, in equations scribbled on chalkboards, and yet our telescopes detect them. Our instruments measure their pulses. Our theories describe their properties. The universe makes things that boggle our intuition and then presents them to us as simple facts. Perhaps the existence of neutron stars can be a kind of permission to accept that not everything needs to fit neatly into our understanding. Some things are simply too extreme for everyday comprehension, and that's all right. We can acknowledge them, marvel at them, and let them drift past us like clouds of an incomprehensible shape. 1 billion tons in a teaspoon. Somewhere out there, gravity has performed this miracle, and the stars keep spinning regardless of whether we can wrap our minds around them. The universe does not require our understanding. It simply is. Here is something that might seem impossible. The universe is expanding faster than the speed of light. At its furthest reaches, in regions so remote that their light has not yet had time to reach us, space itself is stretching outward at a rate that exceeds the cosmic speed limit. And yet, this doesn't violate Einstein's famous rule that nothing can travel faster than light. The key is in understanding what exactly is doing the moving. When we say nothing can exceed the speed of light, we mean nothing can move through space faster than light. A spaceship, a particle, a beam of energy. None of these can outrace a photon as they travel through the fabric of existence. But space itself is not bound by this rule. Space is the stage, not the actor, and the stage can stretch and grow without paying any attention to the speed limits imposed on the things moving across it. The expansion of the universe is not objects flying apart. It is the space between objects growing larger, like dots on a balloon's surface as the balloon inflates. This means there are regions of the universe we will never be able to reach, never be able to see, no matter how advanced our technology becomes. The light from those places will never have time to reach us before the expansion carries them beyond our horizon forever. We are, in a sense, trapped in our own observable bubble, surrounded by an infinity we cannot access. The universe is larger than what we can observe, and it is getting larger every moment. Galaxies that we can see today will eventually be carried beyond our sight, their light stretched into invisibility by the relentless expansion of space. There is something both lonely and liberating in this thought. We cannot have everything. We cannot see everything. The universe keeps secrets from us not out of cruelty, but simply because of geometry, because of the way space and time weave together. And perhaps that's as it should be. Perhaps a universe with no mystery, no hidden places, no regions forever beyond our reach, would be a smaller thing somehow. As you drift toward sleep, you can let the expanding cosmos carry your thoughts outward, knowing that somewhere beyond the horizon, space is growing, always growing, making room for infinities we will never name. Saturn's rings are among the most beautiful structures in our solar system, delicate bands of light encircling a pale golden world, visible even through modest telescopes. They seem solid from a distance, like a disk of smooth material, but up close they reveal themselves to be composed of billions of individual pieces, chunks of ice and rock, some as small as grains of sand, others as large as mountains, all orbiting together in a vast, flat plane around the planet. A cosmic debris field arranged with astonishing precision. The rings span an enormous distance, about 280,000 kilometers from edge to edge. If you could somehow lay them flat across the space between Earth and the Moon, they would stretch most of the way there. And yet, despite this incredible width, they are almost impossibly thin. Most of the ring system is less than a kilometer thick, and in many places, it's only a few tens of meters. If you scaled the rings down to a sheet of paper, they would be far thinner than the paper itself. They are gossamer structures, fragile-seeming veils draped around a giant world. Scientists believe the rings might be relatively young, at least in cosmic terms. Perhaps only 100 million years old, which means they formed long after the dinosaurs walked the Earth. They might be the remains of a moon that wandered too close and was torn apart by Saturn's gravity, its fragments spreading out into the elegant bands we see today. Or perhaps they're the debris from a comet, or the leftovers from the chaotic early days of the solar system. We're still not certain. The rings keep their origins wrapped in mystery, offering us only their beauty as evidence. And the rings are changing, slowly eroding, their particles raining down onto Saturn's atmosphere like a slow, silent snowfall. In another 100 million years or so, they may be gone entirely, and Saturn will be a naked world, stripped of its famous adornment. Future beings looking at our solar system might never know that once there was a planet here wrapped in rings of ice, catching the sunlight and scattering it into rainbows. But for now, they remain, fragile and temporary, and impossibly lovely, like so many of the most precious things. Far from our solar system, orbiting a star in the constellation Vulpecula, there is a planet called HD 18973b. It is a world that looks deceptively peaceful from a distance, a beautiful deep blue color reminiscent of Earth's oceans seen from space. But this resemblance is a cruel illusion. The blue of HD 18973b comes from silicate particles in its atmosphere, tiny grains of glass suspended in clouds of nightmare. And on this world, it rains glass. Sideways. The winds on HD 18973b blow at speeds of 7,000 kilometers per hour, fast enough to circle the Earth in less than 6 hours. These are not breezes, not storms, not anything we have a proper word for in human experience. They are apocalyptic movements of atmosphere, walls of air racing around the planet, with violence that defies our imagination. And carried on these winds, whipped along at impossible speeds, are droplets of molten glass that solidify as they fly, creating a horizontal rain of razor-sharp particles. Every moment on this planet is a bombardment. We cannot go there. We will likely never go there. The planet orbits its star so closely that its surface temperature exceeds 1,000 degrees Celsius, hot enough to melt many metals. It is a world of fire and glass and screaming wind, a place that seems designed to be hostile to anything we would recognize as life or comfort. And yet, from our vantage point 63 light years away, it appears serene, a beautiful blue dot, as peaceful looking as a marble. There is a lesson somewhere in this, perhaps, that appearances can deceive, that beauty and violence can coexist in the same object, that the universe creates things of terrible majesty without caring whether they are habitable or gentle. HD 189733b exists not for us, not for anyone we know of, but simply because the physics of planet formation allowed it to exist. It rains glass there, and no one is harmed, and no one benefits, and the winds howl on eternally. As you settle deeper into your pillow, you can be grateful for the soft rain that falls on Earth, for winds that merely rustle leaves, for a planet that, against all odds, turned out to be gentle enough for creatures like us to lie quietly in the darkness and contemplate creatures like that. In the vastness of space where temperatures already drop to unimaginable depths, there exists a place colder than anywhere else we have discovered, the Boomerang Nebula, located about 5,000 light years from Earth in the constellation Centaurus, holds this remarkable distinction. At just 1 degree above absolute zero, that theoretical basement of temperature where all molecular motion ceases, it is colder than the background temperature of space itself. The universe's ambient temperature, left over from the Big Bang, sits at about 2.7 Kelvin. The Boomerang Nebula somehow manages to be colder than the cosmos that surrounds it. This seems almost paradoxical when you first encounter it. How can something be colder than space? The answer lies in the nebula's rapid expansion. A dying star at the center of the boomerang is expelling its outer layers at tremendous speed, and as this gas rushes outward, it expands so quickly that it cools itself below the temperature of the cosmic microwave background radiation that fills all of space. It's the same principle that makes the air feel cold when it rushes out of a pressurized can, but scaled up to cosmic proportions. The Boomerang Nebula is a place where the ordinary rules of the universe seem temporarily suspended, where a small pocket of existence has managed to become colder than the void itself. It won't last, of course. Eventually, the expanding gas will slow, will absorb energy from the surrounding radiation, will warm back up to match the background temperature of the cosmos. But for now, in this particular moment of cosmic history, there is a place in the universe colder than the universe, a small rebellion against the ambient warmth left over from creation. As you lie here in your own warmth, blankets pulled close against the night, perhaps you can appreciate the comfort of being exactly the right temperature for human existence. Somewhere out there, a nebula shivers at the edge of absolute stillness, colder than cold itself, and you are here, warm and breathing, perfectly positioned in the narrow band of temperatures where life can thrive. Mars glows red in our night sky, a distinctive rusty hue that has captivated human observers for thousands of years. Ancient cultures named it after gods of war, associating its bloody color with conflict and passion. But the truth behind Mars's famous appearance is far more mundane, and perhaps more wonderful for its simplicity. Mars is red because it is rusting. The planet's surface is covered in iron oxide, the same compound that forms when you leave a nail out in the rain. An entire world, slowly oxidizing in the thin Martian air. This rust stretches across nearly the entire planet, coating rocks and sand and ancient volcanic plains in shades of ochre and crimson. When windstorms kick up the fine Martian dust, the sky itself turns pink and salmon, suffused with particles of oxidized iron. Even the sunsets on Mars are different from ours, blue rather than red, an inversion caused by the way Martian dust scatters light. Everything about Mars is painted in the colors of corrosion. But here is what makes this truly remarkable. Rust requires oxygen to form, and oxygen suggests a time when Mars was different. Billions of years ago, Mars likely had a thicker atmosphere, possibly with free oxygen created by volcanic activity or other processes. There may have been water flowing across its surface, rain falling from Martian skies, rivers carving channels through ancient highlands. The rust we see today is a monument to that lost era, a chemical record of a planet that was once more Earth-like than the cold desert it has become. When you look at Mars in the night sky, you're looking at history written in chemistry. Every grain of red sand tells a story of transformation, of a world that changed over billions of years from something potentially habitable to the frozen, rust-covered sphere it is today. And in that story, perhaps, lies a gentle warning and a profound appreciation for our own blue planet, where the conditions for life persist, at least for now. On Jupiter, there is a storm that has been raging for at least 350 years. Longer than any human civilization has continuously recorded history. Longer than many nations have existed. We call it the Great Red Spot, a swirling anticyclone large enough to swallow Earth whole, its rusty clouds churning in bands of crimson and salmon against the planet's striped atmosphere. When Galileo first turned his telescope toward Jupiter in the early 1600s, astronomers of his era may have already glimpsed this tempest. It has been spinning ever since. The Great Red Spot is not like any storm we experience on Earth. Our hurricanes form over warm ocean waters, gather strength, make landfall, and dissipate within weeks. They are temporary visitors, powerful but fleeting. Jupiter's storm has no land to interrupt it, no friction to slow it down, no shortage of energy to sustain it. The planet's rapid rotation and internal heat feed the vortex continuously, keeping it alive across centuries. Generations of humans have been born, lived, and died while this single storm kept turning. And yet, the Great Red Spot is changing. Over the past century, it has been shrinking noticeably, its once vast oval contracting year by year. In the late 1800s, the storm was perhaps 40,000 kilometers across. Today, it's closer to 15,000. Scientists debate whether this means the storm is finally dying, whether in another century or two it might vanish entirely, or whether it's simply going through a natural cycle and will eventually expand again. We don't know. Jupiter keeps its own counsel. There is something almost companionable about a storm that has lasted so long. It has watched over our planet like a distant, churning eye, present throughout the entire span of modern human history. Whatever happens in the years to come, the Great Red Spot has earned its place in our collective imagination, a reminder that some things in the universe operate on time scales that dwarf our brief lives, patient and persistent beyond our comprehension. On Mars, there stands a volcano so large that it challenges our sense of what mountains can be. Olympus Mons rises 21 kilometers above the Martian surface, nearly 2.5 times the height of Mount Everest. Its base spans roughly 600 kilometers, an area comparable to the state of Arizona. If you could somehow transport it to Earth and set it down in the ocean, its summit would extend well into the stratosphere, far above where commercial aircraft fly. But perhaps the most remarkable thing about Olympus Mons is not its height, but its shape. The volcano is what geologists call a shield volcano, built from countless eruptions of fluid lava that spread out in thin layers over millions of years. Its slopes are so gradual, averaging only about 5 degrees, that if you stood on its summit, you would not be able to see its base. The mountain would extend beyond the horizon in every direction, making you feel as though you were standing on a vast, gently tilted plain, rather than atop the largest volcano in the solar system. This is possible on Mars because the planet lacks the plate tectonics that shuffle Earth's crust. On our world, volcanoes form over hot spots in the mantle, but the moving plates carry them away before they can grow too large. Mars has no such mechanism. A volcano can sit over the same hot spot for billions of years, growing and growing without limit. Olympus Mons is what happens when geology has patience, when a mountain is given all the time it needs. Imagine standing there on that impossibly gentle slope, looking out at a horizon that curves away beneath a butterscotch sky. You would know, intellectually, that you were on a mountain, but your senses would tell you otherwise. The universe creates things that exceed our expectations, structures so large they become invisible through their very immensity. Space is silent, completely, utterly, profoundly silent. No matter what science fiction films might suggest with their roaring spacecraft and explosive battles, the cosmos makes no sound at all. Sound requires a medium to travel through: air, water, stone, something for the vibrations to push against and propagate through. In the vacuum of space, there is nothing. Sound waves have nowhere to go. This means that the most violent events in the universe unfold in perfect quiet. When stars explode in supernovae, releasing more energy in a moment than our sun will produce in its entire lifetime, they do so without a whisper. When galaxies collide, their billions of stars interweaving over hundreds of millions of years, the cosmic dance proceeds in absolute stillness. Black holes devour matter, neutron stars collide, gamma-ray bursts flash across the cosmos. All of it happening in silence so complete it borders on the sacred. There is something meditative in this knowledge. We live on a noisy planet, surrounded by the constant hum of activity, traffic and conversation, wind and water, the endless small sounds of being alive. But beyond our thin shell of atmosphere, quiet reigns. The universe does its work without narration, without soundtrack, without the auditory drama we have come to expect from our stories about it. The stars burn silently. The planets orbit silently. The great machinery of the cosmos turns without so much as a creak. Perhaps, as you settle deeper into the stillness of your own room, you can feel a kinship with that cosmic quiet. The silence around you is a small echo of the silence that fills most of existence. In these moments before sleep, you are participating in something the universe knows well, the profound peace of soundlessness, the gentle absence of noise. Mercury, the smallest planet in our solar system and the closest to the Sun, keeps time in a way that seems to defy logic. A single day on Mercury, measured from one sunrise to the next, lasts 176 Earth days. But a year on Mercury, the time it takes to complete one orbit around the Sun, takes only 88 Earth days. This means that on Mercury, a day is twice as long as a year. The Sun rises, and by the time it rises again, the planet has completed 2 full trips around its star. This strange arithmetic arises from Mercury's peculiar rotation. The planet spins very slowly on its axis, taking 59 Earth days to complete one rotation. But because it's also moving quickly around the Sun, the combination of spin and orbit creates this temporal paradox. If you were standing on Mercury's surface, watching the Sun creep across the sky, you would experience the longest days in the solar system, each one stretching on for months by Earth's reckoning. The experience of time there would feel elastic, stretched beyond recognition. Morning would last for weeks. The Sun would hang in the sky, crawling toward noon with geological patience. And then, halfway through your day, Mercury would complete an entire year, passing through all the positions of its orbit while you waited for afternoon to arrive. The concepts of day and year would lose their familiar meaning entirely. Mercury reminds us that time is not fixed, that the rhythms we take for granted, sunrise and sunset, the cycle of seasons, are local phenomena, peculiar to our particular planet. Elsewhere in the cosmos, time moves to different beats, follows different patterns. As you lie here in the comfortable rhythm of Earth time, perhaps there is comfort in knowing that somewhere a planet is slowly turning through days that outlast its years. The International Space Station circles our planet at a speed that seems almost impossible, 28,000 kilometers per hour, completing one full orbit every 90 minutes. At this velocity, astronauts aboard the station do not experience the familiar cycle of day and night that governs life on Earth. Instead, they witness 16 sunrises and 16 sunsets every 24 hours. The Sun emerges from behind Earth's curve, races across the sky, and dips below the horizon again, all in 45 minutes. For the astronauts living and working aboard the station, this creates a strange disconnection from the rhythms of terrestrial life. They cannot rely on the Sun to tell them when to sleep or when to wake. Instead, they follow schedules synchronized with mission control, artificial routines imposed on a world where natural light cycles have become meaningless. They might glance out a window during their morning exercise and see a sunset, then look again an hour later to find the Sun high in an orbital noon. Some astronauts describe this experience as disorienting at first, then oddly liberating. The constant flux of light and dark becomes a kind of visual meditation, a reminder that they have left behind the world where such things seemed fixed and predictable. They are living on a different clock now, a clock defined by velocity rather than rotation, by their orbit around Earth rather than Earth's spin. Imagine floating beside one of those windows, watching the Terminator line, the boundary between day and night, sweep across continents below. India slides from darkness into dawn while you sip your rehydrated coffee. 16 times a day, the world begins again. 16 times, the stars give way to the thin blue arc of atmosphere, and then return. It is a life measured in sunrises, each one a small gift, each one proof that you are moving impossibly fast through the darkness. Galaxies come in shapes. This might seem obvious once stated, but there was a time when we didn't know galaxies existed at all, when those faint smudges in the night sky were thought to be nebulae within our own Milky Way. It wasn't until the 1920s that astronomers confirmed these distant objects were entire island universes, separate from our own, each containing billions of stars. And as we began to study them, we discovered they arranged themselves into distinct categories: spiral, elliptical, and irregular, each shape telling a story of formation and history. Spiral galaxies, like our own Milky Way, display graceful pinwheel arms sweeping out from a central bulge. These arms are regions of active star formation, glowing blue with young, hot stars. Some spirals have bars through their centers, thick bands of stars stretching across the core, which is why our galaxy is classified as a barred spiral. Elliptical galaxies, by contrast, are smooth and featureless, ranging from nearly spherical to elongated like cosmic footballs. They contain older, redder stars and show little ongoing star formation. Irregular galaxies follow no pattern at all, their shapes distorted by gravitational interactions or collisions. These classifications are not merely academic. A galaxy's shape reveals its past, whether it has collided with other galaxies, how quickly it formed its stars, how its dark matter is distributed. The elegant spiral arms indicate density waves sweeping through the galactic disk. The smooth ellipticals often result from mergers, their original structures erased by gravitational chaos. Our own galaxy spins slowly through space, its arms trailing behind like the hem of a vast cosmic dress. Somewhere within one of those arms, in an unremarkable corner of an unremarkable spiral, a small blue planet drifts through its orbit, and on that planet, someone is falling asleep while thinking about the shape of their home. Our sun dominates the solar system in a way that makes everything else seem almost incidental. It contains 99.86% of all the mass in our cosmic neighborhood. Every planet, every moon, every asteroid and comet and grain of dust, all of it together amounts to barely more than a rounding error. If the solar system were a democracy weighted by mass, the sun would win every vote by a margin so vast that opposition would be mathematically meaningless. This overwhelming presence shapes everything about our celestial neighborhood. The sun's gravity reaches out across billions of kilometers, holding planets in their orbits, capturing comets as they fall inward from the distant Oort cloud, defining the very boundaries of what we consider our solar system. Without the sun's gravitational embrace, the planets would drift away into interstellar space, lonely wanderers without a home. Every object here belongs to the sun. Everything else is just visiting. And yet, for all its dominance, our Sun is a perfectly ordinary star. It is a yellow dwarf, middle-aged at 4.5 billion years old, neither particularly large nor particularly small by stellar standards. There are stars that would dwarf our Sun the way our Sun dwarfs Earth. There are stars that burn so faintly they make our Sun seem like a searchlight. In the great census of the galaxy, our Sun is average in almost every way, and that averageness is part of what makes it perfect for life. Consider the vast emptiness of space, the distances between stars, the rarity of planetary systems, and then consider that you exist because one ordinary star happened to form at just the right time, in just the right place, with just the right properties. The Sun asks for no gratitude. It simply burns, as it has for billions of years, as it will for billions more. Of all the planets in our solar system, only one is not named after a god or goddess from ancient mythology. Mercury bears the name of the swift-footed messenger. Venus honors the goddess of love. Mars carries the legacy of the god of war. Jupiter and Saturn, Neptune and Uranus, all named for members of the Roman or Greek pantheons, figures of myth and majesty. But Earth, our own planet, takes its name from something far more humble. It comes from Old English and Germanic words meaning simply ground or soil. We named our world after dirt. There is something touching about this. When our ancestors looked up at the wandering lights in the night sky, they saw mystery and divinity. They imagined those distant points as celestial beings, powerful and unknowable. But when they looked down at the ground beneath their feet, they saw something familiar. The earth they tilled, the soil that grew their food, the land they walked upon each day. They named their home after the most practical, most immediate, most essential thing they knew. This naming happened before anyone understood that Earth was a planet like the others, before anyone realized that those wandering lights were worlds in their own right. By the time we understood our place in the solar system, the name had stuck. We could have renamed it something grander, something more befitting a planet, but we kept the old word instead. Earth, ground, home. Perhaps there is wisdom in that humility. While other planets bear the names of gods, ours reminds us of what we actually are, creatures of the soil, dependent on this thin layer of rock and water and air for everything we have. As you lie here in the darkness, you are lying on earth, which is to say, you are lying on the ground, which is to say, you are exactly where you belong. Here is a fact that has nothing to do with the distant stars, yet everything to do with understanding scale in our universe. There are more molecules in a single glass of water than there are glasses of water in all the world's oceans. Take a moment to let that settle. Every ocean, every sea, every bay and inlet and underwater trench. If you could somehow divide all that water into drinking glasses and count them, you would still have fewer glasses than there are molecules in the one sitting on your nightstand. This seems impossible at first, a trick of language or mathematics, but it speaks to something profound about the nature of reality. The very small is just as vast as the very large. We tend to think of enormity as something out there, in the spaces between galaxies, in the unimaginable distances light must travel. But enormity also exists in the other direction, in the countless particles that make up even the most ordinary objects. A glass of water is a universe unto itself, populated by more citizens than we could ever hope to count. Scientists estimate that a typical glass of water contains roughly 8 septillion molecules. That's an 8 followed by 24 zeros. Meanwhile, all the water on Earth, divided into glasses, would yield perhaps 46 sextillion glasses. A 46 followed by 21 zeros. The molecules win by a factor of thousands. The invisible world inside your drinking glass outnumbers the visible world of all Earth's waters. Scale, it turns out, works wonders in both directions. The universe is not merely large above us. It is also incomprehensibly detailed within us, within everything we touch. As you lie here breathing slowly, countless molecules of air move in and out of your lungs, each one a tiny participant in the vast democracy of matter. You are large, containing multitudes, and you are small, contained by multitudes. Both are true simultaneously. Filling all of space, invisible to our eyes but detectable by sensitive instruments, there is a faint glow left over from the beginning of everything. We call it the cosmic microwave background radiation, and it is the oldest light in the universe, released approximately 380,000 years after the Big Bang, when the cosmos finally cooled enough for atoms to form and for light to travel freely through space. Before that moment, the universe was an opaque fog of plasma. Then suddenly, it became transparent, and light began its long journey. That light has been traveling ever since, for nearly 14 billion years, stretching as space itself expands. What began as brilliant visible light has been redshifted by the expansion into microwaves, a whisper of radiation that fills every corner of the cosmos. No matter where you point a radio telescope, you will detect this faint hum, the afterglow of creation itself, the first light that was ever able to shine. When scientists first discovered this radiation in 1965, they didn't know what they had found. Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, kept detecting a persistent noise they couldn't eliminate. They checked for equipment problems, even cleaned pigeon droppings from the antenna, but the signal remained. Eventually, they realized they were hearing the echo of the Big Bang, a sound so old it predates the existence of stars, planets, or anything we would recognize as structure. Imagine lying beneath a sky filled not just with stars but with this invisible light, this ancient remnant of a time when the universe was young and hot and formless. It surrounds you now, passing through the walls, through your body, through everything. You are bathed in the oldest light that exists, a gentle reminder that you are part of a story that began long before there were stories, long before there was anyone to tell them. Somewhere in the constellation Sagittarius, about 10,000 light years from Earth, there floats a cloud of gas and dust with a rather surprising composition. Sagittarius B2 is a massive molecular cloud, the kind of stellar nursery where new stars are born, and among its many chemical compounds is a staggering quantity of ethyl alcohol. Not methanol, which is poisonous, but ethanol, the same alcohol found in wine and beer and spirits. If you could somehow collect it all, you would have enough to fill 400 trillion pints. This is not a joke or an exaggeration. The alcohol is really there, drifting through space in quantities that boggle the mind. 400 trillion pints would be enough to keep every person on Earth well supplied for billions of years. assuming anyone could figure out how to transport it across 10,000 light years of void. The universe, it seems, has a sense of abundance that borders on the absurd. The alcohol forms through chemistry in the cold depths of space, where simple molecules combine on the surfaces of dust grains and through reactions in the diffuse gas. Ethanol is actually relatively common in molecular clouds, along with other organic compounds that would seem more at home in a chemistry laboratory than in the spaces between stars. These clouds are not just nurseries for stars. They are factories for complex molecules, brewing chemicals in quantities that dwarf anything on Earth. There is something almost whimsical about this discovery. A cosmic pub floating in the darkness, stocked with more drinks than anyone could ever consume. The universe creates without purpose, without audience, producing ethanol in quantities that serve no function except to exist. And here we are, 10,000 light years away, raising a glass in quiet acknowledgement of the strangest bar in the galaxy. Every second, our sun loses approximately 4 million tons of mass. This is not through leakage or evaporation in any conventional sense, but through the process of nuclear fusion at its core. Hydrogen atoms are being crushed together under immense pressure and temperature, fusing into helium, and in that transformation, a small amount of mass is converted directly into energy, according to Einstein's famous equation. That energy is what makes the sun shine. 4 million tons per second sounds catastrophic, as though the sun must be rapidly shrinking, approaching some crisis of depletion. But the sun is vast beyond our everyday comprehension. It contains roughly 2 billion tons of material, a 2 followed by 30 zeros. At its current rate of mass loss, the sun could continue burning for another 5 billion years before exhausting its hydrogen fuel. The loss that seems enormous to us is barely a rounding error to the sun. Consider what this means: the light warming your world, the energy that powers photosynthesis and drives weather patterns and makes life possible, comes from the sun slowly consuming itself. Every sunrise is purchased with solar mass. Every green leaf and warm afternoon represents a tiny fraction of the sun's body, transformed into energy and sent across 93 million miles to reach you. The sun is literally giving itself away, piece by infinitesimal piece, so that we might exist. And yet there is no urgency. 5 billion years is so far beyond human time scales that it might as well be forever. The sun will continue its patient burning long after every worry you have ever had has been forgotten, long after civilizations rise and fall, long after the very concept of worry has become obsolete. It is a generosity measured in eons. When the New Horizons spacecraft flew past Pluto in 2015, it sent back images that revealed something unexpected and strangely moving: a heart-shaped feature on the dwarf planet's surface, bright and smooth against the darker, cratered terrain surrounding it. Scientists named it Tombaugh Regio after Clyde Tombaugh, who discovered Pluto in 1930. This frozen heart, it turns out, is partially composed of nitrogen ice, a substance that behaves almost like a glacial flow on this distant, frigid world. Pluto orbits so far from the sun that temperatures there plunge to around -230 degrees Celsius. At these temperatures, Nitrogen, which on Earth is an invisible gas making up most of our atmosphere, freezes solid and accumulates in vast plains. The heart's left lobe, called Sputnik Planitia, is a basin filled with this nitrogen ice, slowly churning in convection cells like a pot of very, very cold water barely simmering. The ice refreshes itself, erasing craters, keeping the surface young. And on Pluto, it snows. But not water snow, methane snow. The methane in Pluto's thin atmosphere condenses on the peaks of mountains, dusting them white. There is weather on this world, weather we would not recognize, operating under rules that have nothing to do with the water cycle we know. Methane falls from the sky. Nitrogen glaciers creep across basins, and somewhere in the darkness, a frozen heart beats in the only way it can, slowly, patiently, over millions of years. We sent a robot across 3 billion miles to see this heart, and it did not disappoint. Even in the coldest, most distant reaches of our solar system, the universe offers us symbols we cannot help but recognize. Pluto wears its heart on its surface, visible from space, as if it had been waiting all along for someone to notice. Beneath the icy shell of Europa, one of Jupiter's largest moons, there lies an ocean. Not a small sea or a few scattered lakes, but a global ocean containing perhaps twice as much water as all of Earth's oceans combined. This water never sees the sun. It exists in perpetual darkness, trapped beneath a crust of ice that may be 10 to 30 kilometers thick, warmed only by the tidal forces that flex Europa's interior as Jupiter's gravity kneads it like bread dough. This ocean has existed for billions of years, stirred and heated by the push and pull of gravitational forces. Where Europa's rocky mantle meets the water, there may be hydrothermal vents, cracks in the seafloor where hot, mineral-rich water seeps upward into the cold ocean above. On Earth, such vents support entire ecosystems in complete darkness, fed not by sunlight, but by chemical energy. Life there doesn't need the sun. It thrives on chemistry alone. Could something similar exist on Europa? Scientists consider it one of the most promising places in our solar system to search for extraterrestrial life. Not intelligent life, not civilizations, but perhaps microbes, simple organisms that have found a way to exist in that cold, dark water. The ingredients seem to be there: liquid water, energy, and the chemical building blocks that life requires. Whether life actually arose is a question we cannot yet answer. Future missions may one day drill through Europa's ice and lower a probe into that hidden sea. What it finds, or doesn't find, will reshape our understanding of how common life might be in the cosmos. For now, the ocean waits in silence, its secrets preserved beneath miles of frozen water, patient as only a moon can be. The Milky Way and Andromeda galaxies are falling toward each other. Right now, as you lie here in the darkness, the space between our galaxy and our nearest large neighbor is shrinking by about 400,000 kilometers every hour. In approximately 4.5 billion years, these two vast spirals will meet, their arms interweaving, their stars mingling in a gravitational dance that will last for millions of years. This sounds catastrophic, the stuff of disaster movies and apocalyptic scenarios. But here's the remarkable truth. Despite both galaxies containing hundreds of billions of stars each, actual stellar collisions will be extraordinarily rare. The distances between stars are so vast, the space within galaxies so empty, that the two systems will pass through each other like ghosts. Stars will be flung into new orbits, gravitational tides will distort familiar patterns, but the stars themselves will remain largely untouched. Over time, the two galaxies will spiral around each other, gradually merging into a single larger galaxy that astronomers have already nicknamed Milkomeda, or Milkdromeda. Our sun, if it still exists by then, will find itself in a new cosmic neighborhood, orbiting within a structure that no longer resembles either of its parent galaxies. The night sky, if anyone is still there to see it, will be transformed beyond recognition. There is something almost gentle about this cosmic collision. Two island universes embracing across millions of years, reshaping each other without violence, creating something new from their meeting. It is a reminder that even events that sound destructive can be, on the proper timescale, more like dances than disasters. Neptune orbits so far from the Sun that its year stretches across an almost unimaginable span of time. One complete journey around our star takes Neptune approximately 165 Earth years. This means that since Neptune was first discovered in 1846, it has completed only a single orbit. The planet we found is just now returning to roughly the same position in space where astronomers first spotted it, having wandered through the full circle of the zodiac exactly once in all of modern human history. And yet, despite this glacial progress around the Sun, Neptune spins rapidly on its axis. A day on Neptune lasts only about 16 hours, shorter than a day on Earth. This creates an odd contrast, quick days within an enormously long year. Neptune experiences more than 89,000 of its own days in a single Neptunian year, 89,000 sunrises and sunsets, each one bringing the planet only a tiny step further along its vast orbital path. At Neptune's distance, the Sun appears as little more than an extremely bright star. Its warmth is negligible, its gravitational pull weakened by the tremendous gulf of space. And yet the Sun still commands Neptune's motion, still dictates its slow waltz through the outer solar system. Even at the edge of the Sun's influence, the rules of gravity apply. Neptune obeys, patiently tracing its enormous circle. There is perspective to be gained from Neptune's year. Our lives unfold in a fraction of Neptune's orbit. Entire human lifetimes pass while Neptune barely shifts against the background stars. And still the planet continues, unhurried, unconcerned with our timescales, dancing its slow dance in the darkness at the edge of the solar system. Among all the moons in our solar system, Titan stands alone in possessing a substantial atmosphere. Saturn's largest moon is wrapped in a thick, hazy shell of nitrogen and methane that is actually denser than Earth's atmosphere, pressing down on Titan's surface with about 50% more pressure than the air we breathe. If you could stand on Titan, the sky above would not be transparent but a murky orange, sunlight filtered through layers of organic haze that tint everything in shades of amber and rust. This atmosphere creates weather, genuine weather, with clouds and rain and changing conditions. But the rain that falls on Titan is not water. It is liquid methane and ethane, hydrocarbons that on Earth exist as gases, but on Titan, in the bitter cold of minus 179 degrees Celsius, flow as liquids. Methane rain falls from orange skies, filling lakes and rivers that drain into seas. Titan is the only other body in our solar system besides Earth where liquid currently exists on the surface in stable, lasting pools. The Cassini mission and its Huygens probe revealed this alien world in stunning detail. Huygens descended through Titan's atmosphere in 2005, sending back images of a landscape that looked eerily familiar. Rounded pebbles smoothed by flowing liquid, drainage channels cutting through terrain, a surface shaped by processes we recognize even though the materials are utterly foreign. It was like looking at Earth through a strange mirror. Titan reminds us that the building blocks of worlds can combine in unexpected ways. Given the right conditions, even hydrocarbons can create weather and geology, lakes and seasons. The universe is more creative than we often imagine, finding new expressions for familiar phenomena in places we once thought were merely cold and dead. At 100 kilometers above the Earth's surface, there is an invisible boundary that marks where our world ends and space begins. We call it the Kármán line, named after the Hungarian-American physicist Theodor von Kármán, and it represents the altitude at which the atmosphere becomes too thin for conventional aircraft to fly. Above this line, you cannot rely on aerodynamic lift. You must move at orbital velocities, or you will fall. It is, by international agreement, the edge of space. 100 kilometers is not very far. If you could drive your car straight upward, you would reach space in about an hour. It's roughly the distance from one side of a modest city to the other. A journey you might make without much thought on a Sunday afternoon. And yet, those 100 kilometers contain everything that separates the habitability of Earth from the void of the cosmos. Our atmosphere, our weather, our breathable air, our protection from radiation, all of it compressed into a shell thinner than the skin of an apple relative to its size. Above the Kármán line, the rules change. The sky fades from blue to black. Stars become visible even when the sun is shining. The curve of the Earth becomes apparent, that gentle arc that photographs so beautifully from orbit. Everything you have ever known, everyone you have ever loved, every breath you have ever taken, all of it below you, wrapped in that thin blue line of atmosphere, fragile and precious beyond measure. Astronauts who have crossed this boundary often speak of a profound shift in perspective, a recognition of Earth's isolation and beauty that changes them forever. The Kármán line is just a definition, an arbitrary number chosen for convenience. But what it represents, the threshold between home and infinity, is anything but arbitrary. When certain stars reach the end of their lives, they leave behind remnants called white dwarfs, the exposed cores of stars that have shed their outer layers and collapsed under their own gravity. These stellar corpses are extraordinarily dense, packing roughly the mass of our sun into a sphere no larger than Earth. And within some of these white dwarfs, something remarkable occurs. The immense pressure crystallizes carbon into diamond. The heart of a dying star becomes a jewel the size of a world. Astronomers have discovered white dwarfs where the crystallization process is well underway, their interiors solidifying into structures that are, in the most literal sense, enormous diamonds. One such object, informally nicknamed Lucy, after the Beatles' song Lucy in the Sky with Diamonds, sits about 50 light years from Earth. Its core is estimated to be a diamond of roughly 10 billion trillion carats, a number so large it sounds like fantasy rather than astrophysics. These cosmic gems will never be mined, never be held, never catch the light in a jeweler's window. They exist in the darkness between stars, slowly cooling over billions and eventually trillions of years. Their brilliance hidden within shells of degenerate matter. No one will ever see them sparkle, and yet they are there, silent testimonies to the strange beauty the universe creates without audience or purpose. There is something almost melancholy about a diamond that no one will ever see, a jewel formed from the death of a star, cooling in the void for longer than the current age of the cosmos. But perhaps there is also something hopeful, evidence that beauty exists whether or not we witness it, that the universe adorns itself even in places we cannot reach. We call it the North Star, Polaris, the fixed point around which the northern sky appears to rotate. For centuries, sailors have used it to navigate, trusting its steadfast position as a guide through darkness. But Polaris has not always been our pole star, and it will not remain so forever. Earth's axis wobbles slowly over time, like a spinning top beginning to lose momentum. And this wobble, called precession, takes approximately 26,000 years to complete one full cycle. As Earth's axis traces this slow circle through the heavens, it points toward different stars at different times. 12,000 years ago, the pole star was Vega, that brilliant blue-white gem in the constellation Lyra. In about 12,000 more years, Vega will claim that title again. Other stars will serve their terms in between. Thuban, which was the pole star when the Egyptian pyramids were built, Gamma Cephei, which will take over from Polaris in a few thousand years, and others whose names are less familiar. Polaris itself is not precisely at the celestial pole. It's about 2/3 of a degree off, close enough for navigation, but not perfect. And even now, the axis is slowly drifting away from it. The fixity we perceive is an illusion created by human timescales. On the scale of millennia, nothing in the sky is truly fixed. Everything moves, everything changes, everything dances to rhythms too slow for a single lifetime to perceive. The next time you look at Polaris, perhaps you can hold both truths at once, that it serves as a reliable guide for your life, and that it is also temporary, a placeholder in an endless procession of pole stars stretching backward and forward through time. Mercury is the closest planet to the Sun, a scorched world where daytime temperatures soar to over 400 degrees Celsius, hot enough to melt lead, hot enough to vaporize many metals. And yet, at Mercury's poles, in the permanent shadows of deep craters where sunlight has never reached, there is ice, water ice, preserved for billions of years in the coldest places on the hottest planet. This seems paradoxical until you consider Mercury's peculiar geometry. The planet has almost no axial tilt, which means its polar regions receive sunlight at such a shallow angle that the floors of deep craters remain in eternal darkness. Without an atmosphere to distribute heat, these shadowed regions stay bitterly cold, even as the sunlit surface bakes nearby. Temperature differences of hundreds of degrees exist across distances of mere kilometers. The ice likely arrived via comet impacts, water-rich bodies from the outer solar system that crashed into Mercury and deposited their cargo in these frozen refuges. Once there, shielded from the sun's brutal radiation, the ice persisted. It is ancient water, older than human civilization, older perhaps than multicellular life on Earth, waiting in darkness on a world we think of as nothing but heat and rock. Mercury reminds us that extremes can coexist, that fire and ice are not always mutually exclusive. Even on the most inhospitable worlds, pockets of gentleness can persist, hidden from the forces that would destroy them. As you settle deeper into your blankets, perhaps there is comfort in knowing that shelter exists even in the most unlikely places. Humanity has built a machine that travels faster than anything else we have ever created. The Parker Solar Probe, launched in 2018, is on a mission to study the sun's outer atmosphere, and to do so, it must swing repeatedly close to our star, picking up speed with each pass. At its fastest, the probe reaches velocities of approximately 700,000 kilometers per hour, fast enough to travel from New York to Tokyo in under a minute, fast enough to circle the Earth in about 3.5 minutes. This extraordinary speed is achieved through a series of gravitational assists, using Venus as a slingshot to adjust the probe's orbit and send it ever closer to the sun. Each close approach, called a perihelion, brings it nearer than any spacecraft has ever ventured before, skimming through the corona, the sun's outer atmosphere, where temperatures exceed 1,000,000 degrees. The probe survives thanks to an ingenious heat shield that keeps its instruments at room temperature, even as the sunlit side endures unimaginable heat. At these speeds, the probe is exploring a realm where physics becomes visceral. It crosses distances that would take conventional spacecraft years to traverse. It moves faster than any natural object in the solar system, except for particles ejected by the sun itself. In a sense, it has become a kind of honorary solar wind, racing alongside the streams of charged particles that flow outward from our star. We built this thing, this messenger to the sun, this fastest creation of human hands. It carries our questions into the fire and sends back answers through the void. There is something magnificent about that curious, fragile creatures on a small planet can launch their envoys into the heart of a star. Mars experiences dust storms unlike anything on Earth. Our planet's storms are dramatic enough. Hurricanes and tornadoes, blizzards and monsoons, but they are local phenomena, confined to portions of a continent at most. Martian dust storms can grow until they encircle the entire planet, turning day into a dim twilight across a whole world, lasting for weeks or even months before finally subsiding. These global storms begin when the Martian summer heats the atmosphere, lifting fine dust particles into the air. Once aloft, the dust absorbs more sunlight, heating the atmosphere further, lifting more dust, creating a feedback loop that can quickly spiral out of control. The entire planet becomes shrouded in a thick, rust-colored haze that obscures surface features and renders the sky opaque. Rovers on the surface have been forced to hunker down, their solar panels starved of sunlight, waiting for the skies to clear. The 2018 global dust storm lasted for months and was so intense that it contributed to the end of the Opportunity rover's mission. After 15 years of exploration, the rover fell silent during the storm, its batteries depleted, its solar panels coated in dust. When the skies finally cleared, opportunity did not wake up. The storm that had swallowed Mars had also claimed our robotic explorer. There is something humbling about a planet-wide storm. A weather event so vast it becomes a defining feature of an entire world. Mars teaches us that even familiar phenomena, dust, wind, weather, can operate on scales that dwarf our experience. As you listen to whatever wind might be moving outside your window tonight, know that elsewhere, winds are moving entire planets into darkness. Here is a mystery that has puzzled scientists for decades. The sun's corona, its outermost atmosphere, is far hotter than its surface. The visible surface of the sun, called the photosphere, simmers at about 5,500 degrees Celsius, hot enough to vaporize any known substance, but relatively cool by stellar standards. The corona, which extends millions of kilometers into space, reaches temperatures of 1 to 3 million degrees. This seems to violate basic intuition. How can the outer atmosphere be hundreds of times hotter than the surface below it? Imagine standing near a campfire and finding that the air several meters away was thousands of degrees hotter than the flames themselves. It defies our everyday experience of heat, which always seems to dissipate with distance. And yet the sun's corona maintains this impossible temperature, glowing in extreme ultraviolet light, visible during total solar eclipses as a ghostly halo around the darkened disk. Scientists have proposed several explanations. Some point to magnetic reconnection events, where twisted magnetic field lines snap and release enormous energy into the corona. Others suggest that waves traveling along magnetic field lines carry energy outward and deposit it in the upper atmosphere. The Parker Solar Probe is currently investigating this mystery, sampling the corona directly for the first time. What we know for certain is that the universe does not always behave as we expect. Heat does not always flow in simple patterns. The sun's corona remains a reminder that even our nearest star holds secrets we are still working to unravel. Phenomena that challenge our assumptions about how the cosmos operates. Drifting through the darkness between stars, there are planets without suns. We call them rogue planets or orphan planets, worlds that either formed without a parent star or were ejected from their original solar systems by gravitational interactions. They wander alone through interstellar space, carrying no light of their own, warmed by nothing but the faint cosmic background radiation, and perhaps the residual heat of their own formation. Astronomers estimate there may be billions of these rogue planets in our galaxy alone, perhaps outnumbering the planets that orbit stars. They are extremely difficult to detect, since they emit no light and reflect none. We find them occasionally through gravitational microlensing. When a rogue planet passes between Earth and a distant star, briefly magnifying the star's light through the curvature of space-time around the planet's mass. What would it be like on such a world? Eternal darkness? Certainly. No sunrise, no seasons, no warmth from above. Any surface would be frozen to temperatures approaching absolute zero. And yet, some scientists speculate that rogue planets with thick hydrogen atmospheres might retain enough internal heat to keep liquid water beneath their surfaces. Life, if it exists there, would never know that stars exist at all. There is something poignant about these wandering worlds, cast out from the families of planets that orbit in orderly procession, left to drift through the void forever. They are the lonely travelers of the cosmos, the orphans of creation, reminding us that not every world finds a home, yet they persist all the same. The asteroid belt conjures images from science fiction, dense fields of tumbling rocks, spacecraft weaving desperately between deadly obstacles, collisions, and chaos at every turn. The reality is far quieter. The asteroid belt, that great ring of rocky debris orbiting between Mars and Jupiter, is mostly empty space. If you could gather every asteroid in the belt, millions of them, ranging from pebbles to minor planets, their combined mass would be less than 4% of our moon. Spread across that vast orbital region, they leave more emptiness than substance. Spacecraft passing through the asteroid belt rarely need to worry about collisions. The distances between individual asteroids average about 1 million kilometers. And mission planners often don't bother with elaborate avoidance maneuvers. The rocks are simply too sparse, too scattered across too much space to pose a meaningful threat. Several spacecraft have traversed the belt without incident, barely noticing the rocks that supposedly fill it. This emptiness is a consequence of the solar system's size. The asteroid belt spans roughly 150 million kilometers from inner edge to outer edge, an enormous volume that dwarfs the relatively modest amount of material within it. Jupiter's gravity prevented this material from coalescing into a planet, leaving it scattered and dispersed rather than condensed and concentrated. The asteroid belt is yet another reminder that space is mostly space, that even regions we think of as crowded are, by human standards, astonishingly empty. The rocks are there, countless and ancient, but they float in a silence and solitude that our imaginations often fail to capture. Uranus rotates on its side, while most planets spin with their axes more or less perpendicular to their orbital planes. Uranus is tilted at an angle of about 98 degrees, essentially rolling around the sun like a ball rather than spinning like a top. This extreme tilt is unlike anything else in our solar system, and scientists believe it resulted from a cataclysmic collision early in the planet's history, a massive impact that quite literally knocked Uranus over. This sideways orientation creates the most extreme seasons in the solar system. During Uranus's summer solstice, one pole points directly at the sun while the other faces away into darkness. Each pole experiences about 42 years of continuous sunlight, followed by 42 years of continuous night. The transition between these extremes is gradual but relentless, a slow creeping of light and darkness across the planet's blue-green cloud tops. The impact that caused this tilt must have been extraordinary, likely involving an object at least as large as Earth colliding with the young Uranus billions of years ago. Such violence reshaped everything about how the planet experiences its orbit, how its moons are arranged, how its faint ring system is oriented. All of it tilted together, frozen in the aftermath of an ancient catastrophe. Uranus reminds us that the solar system's current arrangement is not inevitable, not preordained. It is the result of contingent events, collisions, and near misses that happen to occur. A different impact, a different angle, and Uranus might spin upright like its neighbors. Instead, It rolls through its orbit alone, bearing the scars of its violent past. In the void of space, temperature behaves in ways that challenge our intuitions. We think of space as cold, and in a sense it is. The background temperature of the universe, that faint glow left over from the Big Bang, is just a few degrees above absolute zero. But temperature in a vacuum is a strange concept, because temperature usually describes the motion of particles, and in space, there are almost no particles to move. An object in space experiences temperature depending on whether it faces the sun or hides in shadow. In direct sunlight near Earth's orbit, a surface can heat to over 100 degrees Celsius. In shadow, it can plunge to minus 150 degrees or lower. There is no atmosphere to distribute this heat, no air to buffer the extremes. The sunlit side bakes while the shadowed side freezes, sometimes on the same object at the same moment. Astronauts on spacewalks experience this duality directly. Their spacesuits must handle temperatures that vary by hundreds of degrees, depending on which side faces the sun. The suits are marvels of thermal engineering, designed to manage heat as carefully as they manage oxygen and pressure. Without them, the unfiltered extremes of space would be quickly lethal. This dual nature of temperature in space, extreme heat and extreme cold, coexisting across distances of centimeters, captures something essential about the void. Space does not average things out. It does not smooth over differences. It holds extremes side by side, waiting for objects to negotiate their own survival in an environment that offers no compromise. Magnetars are a rare type of neutron star, and they possess the most powerful magnetic fields known to exist anywhere in the universe. These fields are roughly a quadrillion times stronger than Earth's magnetic field, a number so large it becomes almost meaningless without context. If you could somehow approach a magnetar, the magnetic field would become lethal long before you reach the surface. At a distance of about 1,000 kilometers, the field would be strong enough to distort the very atoms in your body, disrupting the electromagnetic bonds that hold molecules together. This is not radiation damage or heat or impact. It is something stranger, a force that would stretch and warp the structure of matter itself. The atoms in your tissues would become elongated along the field lines, their electron clouds deformed into shapes incompatible with chemistry as we know it. Life could not exist anywhere near such an object. Even sophisticated machinery would be torn apart at the atomic level. Magnetars form when massive stars collapse in supernovae, leaving behind neutron star cores with unusually powerful magnetic dynamos. They are unstable, prone to violent starquakes that release enormous bursts of gamma rays detectable across the galaxy. A magnetar flare in 2004 was so powerful that it briefly ionized Earth's upper atmosphere from 50,000 light-years away. We felt the touch of a dying star's magnetic field across half the Milky Way. These objects exist at the edge of what physics allows, matter compressed to nuclear densities, magnetic fields amplified to cosmic extremes. They are reminders that the universe creates phenomena far beyond human experience, forces we can measure and describe, but never truly comprehend in any visceral way. When astronomers first began mapping the distribution of galaxies across the sky, they found them clustered in sheets and filaments, separated by vast voids of apparent emptiness. Each galaxy seemed like an island, separated from its neighbors by millions of light years. But the true number of these islands has grown with every improvement in our telescopes. Current estimates suggest the observable universe contains roughly 2 trillion galaxies, a 2 followed by 12 zeros, each one home to billions or trillions of stars. This number keeps increasing as our instruments improve. Deep field observations, where telescopes stare at tiny patches of sky for days or weeks, reveal galaxies too faint and distant to have been seen before. What looks like empty darkness resolves, under sufficient scrutiny, into crowds of ancient light. Every advance in sensitivity discovers more, suggesting the universe is even more densely populated than we previously thought. 2 trillion galaxies. If you could visit one galaxy per second, it would take over 60,000 years to see them all. And each galaxy contains structures and stars and possibly planets beyond counting. The scale of existence becomes impossible to hold in the mind. It is not just large, it is recursively large, vast at every level of magnification, revealing new depths of complexity wherever we look. Perhaps the proper response to such numbers is not comprehension, but surrender, a willingness to accept that we are part of something incomprehensibly larger than ourselves. 2 trillion galaxies spin through the void, and here we are, on one small planet, in one unremarkable galaxy, wondering at it all. Time does not flow at the same rate everywhere. In stronger gravitational fields, time moves more slowly, a phenomenon called gravitational time dilation, predicted by Einstein's general theory of relativity and confirmed by countless experiments since. A clock on the surface of the Earth ticks slightly slower than a clock in orbit, because the Earth's mass curves space-time more strongly at the surface than it does farther away. This effect is tiny in everyday circumstances, a difference of microseconds over years, but it is real and measurable. The GPS satellites orbiting Earth must account for gravitational time dilation in their calculations. Without corrections, the navigation system would drift by kilometers per day. The practical functioning of modern technology depends on Einstein's century-old insights about the nature of space-time. Near more extreme objects, the effect becomes dramatic. At the event horizon of a black hole, time slows to a standstill relative to distant observers. An astronaut falling toward a black hole would, from their own perspective, cross the event horizon in finite time. But to someone watching from safely outside, that astronaut would appear to slow down, redden, and fade, never quite reaching the horizon, frozen there for eternity at the threshold of infinity. Time, it turns out, is not the fixed backdrop we experience it to be. It is woven into the fabric of space-time, responsive to mass and energy, flowing differently depending on where you stand. As you lie here in Earth's modest gravity well, time flows just slightly slower for you than it does for the satellites overhead. You are, in the most literal sense, aging at a different rate than the machines orbiting above. If you could zoom out far enough to see the universe at its largest scales, you would find that galaxies are not scattered randomly through space. Instead, they are arranged along vast filaments and sheets that form a structure astronomers call the cosmic web. These filaments stretch for hundreds of millions of light years. with galaxies clustered at the intersections like dewdrops on a spider's web. Between the filaments lie enormous voids, regions of space almost entirely empty of galaxies, some spanning hundreds of millions of light years across. This structure emerged from tiny fluctuations in the density of matter in the early universe. Where matter was slightly denser, gravity pulled in more matter, gradually amplifying small differences into the grand architecture we see today. The cosmic web is the universe's skeleton, the framework on which everything else hangs. Galaxies flow along its filaments, like blood through capillaries, drawn by gravity toward the great clusters at the nodes. The pattern resembles structures we see in other complex systems: neural networks, the internet, slime mold networks, the distribution of blood vessels in living tissue. There seems to be something universal about this web-like organization, some deep mathematical principle that governs how connected systems arrange themselves across scales. The universe has chosen a form that echoes through countless other domains. When you imagine the cosmos, try to hold this image. Not scattered points of light in empty darkness, but a vast web of luminous threads stretching in every direction, with the darkness between them not mere emptiness, but structured void, shaped by the presence of what surrounds it. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep through space like the rotating beam of a lighthouse. If Earth happens to lie in the path of the beam, we detect regular pulses of radio waves, X-rays, or other radiation, pulses so precise that when the first pulsar was discovered in 1967, astronomers briefly wondered if they had detected a signal from an intelligent civilization. Some pulsars spin at almost unbelievable rates. Millisecond pulsars complete hundreds of rotations per second, their surfaces moving at a significant fraction of the speed of light. Despite this incredible spin, their pulses remain extraordinarily regular, more precise than atomic clocks, stable over millions of years. This regularity has made pulsars useful as cosmic timekeepers, their signals serving as reference points for testing theories of gravity and searching for gravitational waves. The pulsar at the heart of the Crab Nebula spins about 30 times per second and has been slowing down gradually since its formation in a supernova observed by Chinese astronomers in 1054 CE. That explosion was visible in daylight for weeks, bright enough to read by at night. Now, almost 1,000 years later, we can still detect the rapidly spinning core left behind, still emitting its lighthouse beam across the galaxy. These cosmic lighthouses will eventually slow and fade, their beams weakening as they radiate away their rotational energy. But for now, they pulse through the darkness, keeping time for the universe, beacons that neither know nor care that distant creatures have learned to detect their rhythm. At the very center of our galaxy, hidden behind clouds of gas and dust that block visible light, there lurks a supermassive black hole. We call it Sagittarius A, and it contains the mass of approximately 4 million suns compressed into a region smaller than Mercury's orbit around the Sun. It is the gravitational anchor around which the entire Milky Way rotates, the hidden heart of our cosmic home. Despite its enormous mass, Sagittarius A is surprisingly quiet. Unlike the supermassive black holes at the centers of some galaxies, which devour matter voraciously and blaze with the light of billions of stars, our black hole is relatively dormant. It consumes matter only occasionally, flaring briefly when a cloud of gas or an unlucky star wanders too close. Most of the time, it sits in darkness, patient and still, its presence known only by its gravitational influence on the stars that orbit nearby. Astronomers have tracked stars near the galactic center for decades, watching them trace enormous ellipses around an invisible point. Some of these stars swing within a few billion kilometers of the event horizon, close enough to experience significant time dilation, close enough to reach speeds of several percent of the speed of light. Their motions provided conclusive evidence that a supermassive black hole must be there, an object so massive and compact that no other explanation fits the observations. The black hole will remain there long after our sun has died, long after the Milky Way has merged with Andromeda, still anchoring whatever galaxy exists in the far future. It is ancient, patient, and nearly eternal, the quiet giant that has watched over our galaxy since its earliest days. Right now, as you lie here in the darkness, particles from distant cosmic catastrophes are passing through your body. Cosmic rays, high-energy protons and atomic nuclei, rain down on Earth continuously, created by exploding stars, active galactic nuclei, and other energetic phenomena across the universe. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but some reach the surface, and a few pass through everything in their path, including you. These particles travel at nearly the speed of light, carrying energies millions or even billions of times greater than anything our particle accelerators can produce. When they strike the upper atmosphere, they create cascades of secondary particles that shower down to ground level. Several of these secondary particles pass through your body every second, leaving tiny trails of ionization in your tissues, invisible tracks recording the distant violence of the cosmos. This is not dangerous in any practical sense. The radiation dose from cosmic rays at sea level is far lower than what we receive from natural background sources on Earth. But there is something profound in knowing that you are constantly being touched by particles born in stellar explosions halfway across the galaxy. You are not isolated from the universe. It reaches into you, through you, leaving traces of its energy in your cells. As you breathe and drift toward sleep, cosmic rays continue their silent passage, oblivious to the bodies they traverse, carrying messages from events that occurred millions of years ago in places we will never visit. You are, in this small way, part of the cosmic circulation of matter and energy. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky and left the shutter open for 10 consecutive days. The target was chosen specifically because it appeared to contain nothing. No bright stars, no known galaxies, just darkness. What came back from that long exposure changed our understanding of the universe forever. That tiny patch, smaller than a grain of sand held at arm's length, contained approximately 3,000 galaxies. This image, called the Hubble Deep Field, revealed that what looks empty to our eyes is actually crowded with ancient light. Each galaxy in the image contains billions of stars, and many of those galaxies lie billions of light years away, their light having traveled for most of the age of the universe to reach Hubble's mirror. We were seeing the past, galaxies as they were when the universe was young, when stars were forming at rates far higher than today. Subsequent deep field images using improved instruments and longer exposures have revealed even more galaxies in similar patches of sky. The universe we now understand is far more densely populated than anyone had imagined before these observations. There is no truly empty direction to look. Everywhere we point our telescopes, we find more light, more structure, more worlds than we can count. The night sky appears mostly dark because our eyes are limited instruments, sensitive to only a narrow range of wavelengths and unable to accumulate light over long exposures. But the darkness is an illusion. The universe is filled with galaxies, packed so densely that even the emptiest looking patches overflow with light if we only look long enough and carefully enough. Enceladus is a small moon of Saturn, barely 500 kilometers across, a body you could drive around in less than a day on Earth's highways. It should be a frozen, dead world, too small to retain internal heat, too distant from the sun to experience any warmth. And yet, from fractures near its south pole, enormous geysers of water ice and vapor erupt continuously into space, shooting hundreds of kilometers above the surface before falling back as snow or escaping into orbit around Saturn. These geysers draw their material from a global ocean of liquid water hidden beneath Enceladus's icy crust, an ocean that shouldn't exist by all conventional reasoning. The heat that keeps this water liquid comes from tidal forces, the constant flexing of Enceladus's interior as Saturn's gravity kneads it like dough. This tidal heating is enough to maintain liquid water billions of kilometers from the sun in one of the coldest regions of the solar system. The Cassini spacecraft flew through these plumes multiple times, sampling their contents directly. It found water vapor, ice crystals, salts, and organic molecules, the ingredients that, on Earth, are associated with the emergence and sustenance of life. Hydrothermal activity at the ocean floor may provide energy for potential ecosystems, just as hydrothermal vents support life in Earth's deep oceans. Enceladus has become one of the most intriguing targets in the search for life beyond Earth. A small, icy moon that should have frozen solid billions of years ago is instead alive with geological activity, spraying the evidence of its hidden ocean into space for anyone who cares to look. Nothing can travel faster than light. This is not merely an engineering limitation or a technological barrier we might someday overcome. It is woven into the fundamental structure of space-time itself. The speed of light, exactly 299,792,458 meters per second, is a cosmic speed limit that no particle, no signal, no information can exceed. This number shapes everything about how the universe operates, from the delay in communications across the solar system to the very nature of causality itself. As an object with mass approaches the speed of light, something strange happens. The energy required to accelerate it further increases without limit. To actually reach the speed of light, an infinite amount of energy would be required, a physical impossibility. Only massless particles, like photons, can travel at light speed, and they can never travel at any other speed. They are born at light speed and exist at light speed until they are absorbed or destroyed. This speed limit has profound implications for the universe we inhabit. It means that information cannot travel instantaneously. It means that distant events cannot affect us until their light has had time to arrive. It means that the observable universe has a horizon beyond which we cannot see, because light from those regions has not yet had time to reach us since the Big Bang. The speed of light seems arbitrary in its precise value, yet it underpins everything about causality and physics. It is the fundamental tempo of the cosmos, the beat to which all of existence must march, a limit that feels less like a constraint and more like a defining feature of reality itself. Galaxies are not static islands drifting peacefully through the void. They interact, collide, and sometimes consume one another in slow-motion mergers that unfold over hundreds of millions of years. Our own Milky Way is currently in the process of cannibalizing several smaller galaxies, drawing their stars into its gravitational embrace and absorbing them into its structure. The evidence of these cosmic meals is written across our sky in streams of stars that don't quite belong. The Sagittarius Dwarf Elliptical Galaxy is one such victim, a small galaxy that has been orbiting the Milky Way and gradually being torn apart by tidal forces. Its stars are being stretched into long streams that wrap around our galaxy like ribbons, slowly incorporated into the larger structure. In a few 100 million years, the Sagittarius Dwarf will cease to exist as a separate entity. Its stars will simply become part of the Milky Way, their origins forgotten except by astronomers who traced their unusual orbits. Other stellar streams crisscross our galaxy, remnants of dwarf galaxies consumed long ago. The Milky Way has been eating its neighbors for billions of years, growing larger with each acquisition. This is not unusual. Most large galaxies have similar histories of mergers and acquisitions, building themselves up through cosmic cannibalism over the age of the universe. There is something almost organic about this process, the way larger structures consume smaller ones and grow, the way the universe tends toward consolidation over time. Galaxies are not merely collections of stars, but living systems in their own right, with histories of interaction and absorption that shape their present forms. Phobos, the larger of Mars's two small moons, is doomed. Every century, it drifts about 2 meters closer to the red planet, drawn inward by tidal forces that are slowly but inexorably shrinking its orbit. In approximately 50 million years, a blink of an eye by cosmic standards, Phobos will either crash into Mars or, more likely, be torn apart by tidal stresses as it crosses the Roche limit, the distance at which a moon can no longer hold itself together against its planet's gravity. If Phobos disintegrates, its debris will spread into a ring around Mars, transforming the planet into a miniature Saturn for a geological moment. Eventually, that ring will rain down onto the Martian surface, adding a thin layer of moon dust to the already dusty landscape. Mars may have had rings before, formed from the destruction of previous moons, and may have rings again after Phobos is gone. Phobos itself is a strange object, heavily cratered, potato-shaped, only about 22 kilometers across at its widest. Its surface is marked by parallel grooves whose origin remains debated, possibly fractures from the tidal stresses that are slowly killing it. The moon circles Mars 3 times per Martian day, rising in the west and setting in the east, moving faster than Mars rotates. The fate of Phobos is written in orbital mechanics, as certain as any prediction in astronomy. It is a reminder that the current arrangement of the solar system is temporary, that moons are gained and lost, that even celestial bodies have lifespans. 50 million years is longer than humans have existed as a species, yet it is brief enough that Mars will look noticeably different when it arrives. The James Webb Space Telescope, launched in 2021, is the most powerful infrared observatory ever placed in space. Its primary mirror, over 6 meters across and coated in gold, is designed to capture infrared light, the heat signatures of distant objects, the glow of stars forming within dusty cocoons, the red-shifted light of the earliest galaxies in the universe. With unprecedented sensitivity, it can detect the heat of a bumblebee at the distance of the moon. This sensitivity matters because the oldest light in the universe has been stretched by cosmic expansion into infrared wavelengths. To see the first galaxies, we need infrared eyes. Webb provides them, peering through the cosmic dust that blocks visible light, and detecting objects too faint and too red for any previous telescope to discern. Its images reveal galaxies forming when the universe was only a few 100 million years old, young systems taking shape in the cosmic dawn. The telescope orbits the Sun at a point called L2, about 1.5 million kilometers from Earth, where it remains perpetually in Earth's shadow. A massive sunshield protects its instruments from solar radiation, keeping them chilled to temperatures near absolute zero. This extreme cold is necessary because infrared astronomy is essentially the detection of heat, and any warmth in the telescope itself would overwhelm the faint signals from distant stars. Webb has already transformed our understanding of the early universe, revealing that galaxies formed earlier and grew larger than previous theories predicted. Each image it returns rewrites some chapter of cosmic history, adding detail and nuance to our story of how everything began. Some stars are moving so fast they will escape the Milky Way entirely. These hypervelocity stars race through the galaxy at speeds exceeding 1,000 kilometers per second. Fast enough to break free from our galaxy's gravitational grasp and sail off into intergalactic space forever. They are rare, perhaps a few hundred in the entire galaxy, but their existence tells us something dramatic about the forces at play near the galactic center. Most hypervelocity stars are thought to originate from close encounters with the supermassive black hole at the center of the Milky Way. When a binary star system wanders too close to Sagittarius A, the black hole's immense gravity can capture one star while flinging the other outward at tremendous speed. The captured star spirals inward, possibly to be consumed, while its former companion rockets toward the galactic rim, never to return. Other mechanisms can produce hypervelocity stars as well. Supernova explosions in binary systems, gravitational interactions in dense star clusters, encounters with intermediate mass black holes. But the galactic center remains the primary source, a cosmic slingshot that occasionally hurls stars into exile. These stars will eventually leave the Milky Way entirely, drifting into the vast emptiness between galaxies. They will carry no planets, no companions, no hope of interaction with other stars for billions of years. They are the ultimate wanderers, exiled by gravity to spend eternity in the darkness between islands of light, The universe is 13.8 billion years old. This is not an estimate or a guess, but a measurement, derived from multiple independent lines of evidence that all converge on the same answer. The cosmic microwave background radiation, the oldest light in the universe, carries information about the age and composition of the early cosmos. Observations of distant supernovae reveal the expansion history of the universe. The abundances of light elements tell us about conditions in the first few minutes after the Big Bang. All of these methods agree. This precision is remarkable given the vastness of what we're trying to measure. We are determining the age of everything, every star, every galaxy, every atom, every moment of time that has ever existed, and we know it to within about 1% uncertainty. The universe is 13.8 billion years old, give or take a few tens of millions of years. In cosmic terms, that margin of error is almost insignificant. This age sets the stage for everything else. Stars have been forming and dying for most of this time. Galaxies have been merging and evolving. Heavy elements have been building up, generation after generation of stars, until the universe became chemically complex enough for planets like Earth to form. We are latecomers to a story that has been unfolding for almost 14 billion years. When you look at the night sky, you are looking at history. The light from distant stars takes years or centuries or millennia to reach you. The light from distant galaxies takes millions or billions of years. You are seeing the universe at many different ages simultaneously, a layered view of cosmic time stretching back toward the beginning. Io, the innermost of Jupiter's 4 large moons, is the most volcanically active body in our solar system. Its surface is constantly being renewed by eruptions, lava flows, and volcanic plumes that shoot hundreds of kilometers into space. There are no impact craters visible on Io because they are erased almost as quickly as they form, buried under fresh volcanic material. The moon's surface is a patchwork of yellows, oranges, and reds, the colors of sulfur and its compounds, deposited by continuous volcanic activity. This volcanism is driven by tidal heating. Io orbits close to Jupiter, locked in gravitational resonances with other moons that prevent its orbit from becoming perfectly circular. As a result, Io is constantly being flexed and squeezed by Jupiter's gravity, its interior heated by friction, like a handball being repeatedly compressed. This generates enough heat to melt rock and drive volcanic activity that dwarfs anything on Earth. The Voyager spacecraft discovered Io's volcanism in 1979, when navigation engineer Linda Morabito noticed a strange protrusion on the moon's limb in one of the images. It was a volcanic plume caught in the act of erupting, the first active extraterrestrial volcanism ever observed. Since then, spacecraft have documented hundreds of active volcanoes on Io, some erupting continuously for decades. Io is a world in constant turmoil, its surface perpetually young, its geology driven by forces we rarely experience on our stable, quiet Earth. It is a reminder that planetary bodies can be violent, dynamic places, even without atmospheres or oceans or any of the other features we associate with geologic activity. About 85% of all matter in the universe is invisible to us. We call it dark matter, not because we know what it is, but because we know what it isn't. It doesn't emit light, absorb light, or interact with electromagnetic radiation in any way we can detect. We know it exists only through its gravitational effects, the way it bends light from distant galaxies, the way it influences the rotation of spiral arms, the way it shapes the large-scale structure of the cosmos. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. Without dark matter, their outer stars would fly off into space, dispersed by centrifugal force. The fact that galaxies remain coherent tells us something massive must be there, something we cannot see, providing the extra gravitational glue that holds everything together. Dark matter forms halos around galaxies, extending far beyond the visible disk of stars. Despite decades of searching, we have never directly detected a dark matter particle. We have built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to bump into an ordinary atom. We have searched for dark matter signatures in particle accelerator experiments. We have looked for the products of dark matter annihilation in space. So far, nothing conclusive. The identity of dark matter remains one of the greatest unsolved mysteries in physics. We know it's there. We can measure its effects with precision, but we cannot see it, cannot touch it, cannot capture it in our laboratories. The majority of matter in the universe remains hidden from us, a shadow that shapes everything we see. Our sun is approximately 4.6 billion years old, almost exactly halfway through its expected lifetime. Like a person settling into middle age, it has passed through its turbulent youth and settled into a long period of stability, burning hydrogen steadily in its core, maintaining a consistent output of energy that has allowed life on Earth to evolve and flourish. The sun will continue this steady burning for another 5 billion years or so before beginning its transformation into something else. In its youth, the sun was somewhat fainter than it is today, about 70% as luminous. This faint young sun paradox puzzled scientists for years, since Earth should have been frozen solid under such reduced illumination. Yet geological evidence shows liquid water existed from very early on. The resolution likely involves greenhouse gases in Earth's early atmosphere, trapping enough heat to keep water liquid despite the weaker sunlight. Over the coming billions of years, the sun will gradually brighten as it ages, eventually becoming uncomfortable for life on Earth long before it exhausts its hydrogen fuel. In about 1 billion years, the increased luminosity may trigger a runaway greenhouse effect, evaporating the oceans and transforming Earth into something resembling Venus. Life, if it still exists, will need to adapt or relocate. But for now, we live in the sun's golden age, a period of stability that may last longer than complex life has existed on Earth. The sun asks nothing of us in return for its constancy. It simply burns, as it has since before there were eyes to see its light. Enceladus, that small, icy moon of Saturn, does something remarkable. It broadcasts evidence of its interior directly into space. The geysers erupting from its south pole don't just create a beautiful spectacle. They offer scientists a way to sample the moon's hidden ocean without ever landing on the surface. The Cassini spacecraft flew through these plumes multiple times, tasting the ocean of another world from orbit. What Cassini found was tantalizing. The plumes contain water vapor and ice crystals as expected, but also salts that suggest prolonged contact between water and rock. the kind of water-rock interaction that provides chemical energy for life on Earth. Even more intriguing, Cassini detected molecular hydrogen in the plumes, a possible sign of hydrothermal activity on the ocean floor. On Earth, hydrothermal vents support entire ecosystems in the absence of sunlight. The organic molecules found in the plumes add another layer of intrigue. While the presence of organics doesn't prove life exists, it does demonstrate that the chemistry of life's building blocks is present in Enceladus's ocean. The ingredients are there: liquid water, chemical energy, organic compounds, and time. Whether life has actually emerged remains unknown, but the conditions appear favorable. Future missions may return to Enceladus to study its plumes in greater detail, or even to land on the surface and drill through the ice. For now, we are left with the extraordinary fact that this tiny moon is voluntarily sharing samples of its ocean with anyone who cares to catch them. On a clear, dark night, away from city lights, you can see the Andromeda Galaxy with your naked eyes. It appears as a faint smudge of light in the constellation Andromeda. Easy to miss if you don't know where to look, but unmistakable once you find it. That smudge is not a star or a nebula within our own galaxy, but an entirely separate island universe containing roughly 1 trillion stars, located 2.5 million light-years away. When you see Andromeda, you are seeing light that began its journey 2.5 million years ago, long before anatomically modern humans existed. Our ancestors at that time were just beginning to develop stone tools, their brains smaller than ours, their lives unimaginably different from anything we know today. The light that left Andromeda when they lived is only now arriving at your eyes, having traveled through the void for all of human prehistory. Andromeda is the most distant object visible to the unaided human eye under normal conditions. Everything else you can see in the night sky, every star, every planet, every fuzzy patch of nebula, lies within our own Milky Way galaxy, mere tens of thousands of light-years away at most. Andromeda alone offers a glimpse of the true scale of the universe, a reminder that what we see overhead is only one galaxy among trillions. And yet, despite its distance, Andromeda feels almost close, a neighbor galaxy, falling toward us at 400,000 kilometers per hour, destined to merge with the Milky Way in the distant future. That faint smudge of light is both impossibly far and surprisingly near, depending on your frame of reference. In the vast census of stellar systems, there exist pairs of stars so close together that they share a common envelope of gas. These contact binaries orbit each other so tightly that their outer atmospheres merge, creating a peanut-shaped or dumbbell-shaped object where two stellar cores swim within a single shared skin. They are no longer quite two stars, yet not quite one. Something in between, an intimate partnership written in plasma and light. These systems form when two stars in a closed binary evolve and expand, their outer layers swelling until they touch and merge. Once contact is established, matter flows between the two stars, equalizing their temperatures and compositions, binding them even more tightly together. The orbital periods of contact binaries can be remarkably short. Some complete an orbit in less than a day, the two stars whirling around their common center of gravity in a perpetual embrace. Over time, many contact binaries will spiral even closer together, losing energy and angular momentum until they eventually merge into a single, rapidly rotating star. This merger can be gentle or violent, sometimes producing a luminous red nova, a burst of light as two stars become one. The universe is full of such stellar marriages, partnerships that end in union rather than separation. There is something almost romantic about contact binaries, if we allow ourselves to anthropomorphize for a moment. Two stars that drew close enough to share everything, their fates intertwined, their futures inseparable. They will either merge into one or be torn apart by the forces they generate. But for now, they dance together in the darkness, closer than any other stars can be. The sun does not merely shine, it breathes outward, exhaling a constant stream of charged particles called the solar wind. This wind flows outward from the sun's corona at speeds averaging about 400 kilometers per second, filling the solar system with a thin plasma of protons, electrons, and heavier ions. It is not wind in any earthly sense, not a movement of air, but a river of particles rushing away from our star in all directions. The solar wind shapes the environment of every planet it touches. It sculpts the tails of comets, always pointing away from the sun regardless of which direction the comet is traveling. It compresses Earth's magnetic field on the sunward side and stretches it into a long tail on the night side. When particularly intense gusts of solar wind, coronal mass ejections, strike Earth's magnetic field, they can trigger geomagnetic storms, disrupting radio communications and power grids while painting the polar skies with auroras. At the edge of the solar system, the solar wind finally slows and stops, its outward pressure balanced by the pressure of interstellar gas. This boundary, called the heliopause, marks where the sun's direct influence ends and interstellar space begins. Voyager 1 crossed this threshold in 2012, becoming the first human-made object to leave the sun's domain and enter the space between stars. The sun's exhalation reaches across billions of kilometers, shaping the environment of worlds it will never touch directly. Even here, in the darkness before sleep, you exist within the heliosphere, the bubble of solar wind that defines our home in the galaxy. Red dwarfs are the most common type of star in the universe, yet not a single one is visible to the naked eye from Earth. These small, cool stars burn their hydrogen fuel so slowly and so efficiently that they will shine for trillions of years, far longer than the current age of the universe. They are the tortoises of the stellar world, outlasting their brighter, more spectacular cousins by almost unimaginable margins. The dimmest red dwarfs produce only a few thousandths of the sun's luminosity, glowing a deep crimson that would render any orbiting planets in perpetual twilight. They are so faint that even the nearest red dwarf, Proxima Centauri, requires a telescope to see despite being only 4.2 light-years away. The night sky appears dominated by hot, bright stars, not because they're common, but because they're visible. The vast majority of stars are red dwarfs lurking below the threshold of human perception. Because red dwarfs burn so slowly, none of them have ever died of old age. Every red dwarf that has ever formed is still shining today, accumulating over the entire history of the universe. In the far future, when stars like our sun have long since burned out, red dwarfs will continue their patient glow. the last lights in an increasingly dark cosmos. They will witness the end of star formation, the cooling of galaxies, the slow fade toward heat death, still burning when almost everything else has gone dark. These unassuming stars may be the most important objects in the universe's long-term future, the final repositories of light and warmth in an aging cosmos. Their dimness is, in a sense, their gift to eternity. For decades, scientists defined the habitable zone around a star as the region where liquid water could exist on a planet's surface. Not too hot, not too cold, the so-called Goldilocks zone. But this definition has proven too narrow. We now know that habitability extends far beyond these simple temperature boundaries, that life might find a way in places we once dismissed as hopelessly hostile. Moons like Europa and Enceladus maintain liquid water beneath their icy surfaces, warmed not by sunlight, but by tidal heating from their parent planets. Titan possesses liquid hydrocarbon lakes and a thick atmosphere, with some scientists speculating that exotic biochemistries might function in such an environment. Even rogue planets drifting between stars might harbor subsurface, oceans kept liquid by residual heat, and thick hydrogen atmospheres that trap warmth through pressure-induced infrared absorption. The concept of habitable zones is expanding to include not just distance from a star, but also the presence of geological activity, the thickness of atmospheres, the influence of nearby moons and planets, and chemistry we have only begun to imagine. Life on Earth thrives in boiling hot springs and freezing Antarctic ice, in crushing deep sea pressures and toxic acidic pools. The limits of life seem to expand with every extreme environment we explore. Perhaps habitability is less about finding Earth-like conditions and more about finding energy gradients and chemistry that life can exploit. The universe may be far more hospitable than we once believed, its potential for life lurking in places we never thought to look. When massive objects accelerate, when black holes collide, when neutron stars spiral together, when stars explode asymmetrically, they create ripples in space-time itself. These gravitational waves propagate outward at the speed of light, stretching and compressing space as they pass, carrying information about the violent events that created them. Einstein predicted their existence in 1915, but it took a century before we developed instruments sensitive enough to detect them. The first direct detection came in September 2015, when the LIGO observatories in Louisiana and Washington recorded the signature of two black holes merging 1.3 billion light-years away. The signal lasted a fraction of a second, a chirp of rising frequency as the black holes spiraled together, followed by silence as they merged into one. In that brief moment, an entirely new way of observing the universe was born. Gravitational wave detectors work by measuring impossibly small changes in distance. LIGO's laser beams travel down 4-kilometer-long arms, bouncing between mirrors and recombining to create interference patterns. When a gravitational wave passes, it stretches one arm while compressing the other, shifting the interference pattern by a distance smaller than the width of a proton. The precision required to detect such a signal is almost beyond comprehension. Since that first detection, we have heard the cosmos ring with gravitational waves from dozens of merging black holes, colliding neutron stars, and other violent events. We are no longer limited to seeing the universe through light alone. We can now feel its vibrations, listen to its tremors, sense the ripples it sends through the very fabric of existence. Beyond the orbit of Neptune, far past the Kuiper Belt where Pluto resides, there is thought to exist a vast spherical shell of icy bodies called the Oort cloud. This hypothetical structure extends from roughly 2,000 astronomical units from the Sun to perhaps 100,000 astronomical units, nearly a quarter of the way to the nearest star. No spacecraft has visited it, no telescope has directly observed it. Yet mathematical models strongly suggest it must be there. The Oort cloud is believed to be the source of long-period comets, those visitors from the outer dark that appear in our skies on orbits lasting thousands or millions of years. Something disturbs these icy bodies, a passing star perhaps, or the gravitational influence of the galaxy itself, and sends them falling inward toward the sun. They spend millennia falling through the darkness before finally blazing briefly to life as comets in the inner solar system. The objects in the Oort cloud are remnants from the formation of the solar system, icy planetesimals that were scattered outward by gravitational interactions with the giant planets. They have drifted in the cold outer reaches for 4.5 billion years, preserved in deep freeze, waiting for some perturbation to send them sunward. Many will wait forever, never disturbed, never warmed, never seen. The existence of the Oort cloud reminds us how much of our solar system remains unexplored and even unobserved. We infer its presence from the comets that fall from it, tracing their orbits backward into the darkness and concluding that something must be out there. It is a ghost structure, known only by its messengers, among the thousands of exoplanets discovered beyond our solar system. Some orbit their stars so closely that their years last only hours. These ultra-short period planets whirl around their stars at breathtaking speeds, completing full orbits in the time it takes to watch a movie or eat a leisurely dinner. Their surfaces, baked by proximity to their stars, can reach temperatures of 2,000 degrees Celsius or more, hot enough to vaporize rock and create atmospheres of silicon and metal vapors. These close-in planets puzzle astronomers because they couldn't have formed where we find them. So near to their stars, there wasn't enough material to build them, and the heat would have prevented rocky bodies from condensing in the first place. They must have migrated inward from more distant orbits, spiraling closer over millions of years through interactions with their planetary systems, or the disks of gas and dust from which they formed. Some of these planets are so close to their stars that they are being actively destroyed. Their atmospheres boil away into space, leaving behind tails of escaping gas that trail behind them like cometary streamers. They are slowly evaporating, losing mass with each orbit, their lifetimes measured in millions rather than billions of years. We may be seeing them in their death throes, the final phase before they disintegrate entirely or spiral into their stars. The existence of these extreme worlds challenges our understanding of planetary system architecture. The gentle, orderly arrangement of our solar system is not universal. Other systems are far more chaotic, their planets crowded close together in configurations we once thought impossible. There is a boundary in space where the sun's influence finally yields to the forces of the interstellar medium. This boundary, called the heliopause, marks the edge of the heliosphere, the bubble of solar wind that surrounds our star and defines our cosmic neighborhood. Beyond it lies interstellar space, the vast emptiness between stars, where the sun is just another point of light among billions. The heliopause lies about 120 astronomical units from the sun, roughly 4 times the distance to Neptune. At this distance, the outward pressure of the solar wind becomes too weak to push back against the inward pressure of interstellar gas and cosmic rays. The two forces balance, creating a boundary that fluctuates slightly as the sun's activity waxes and wanes, but remains remarkably stable overall. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. Both spacecraft continue to transmit data, their signals taking over 20 hours to reach Earth, describing conditions in a region no instrument had ever sampled directly. They carry golden records bearing sounds and images from Earth, messages for any intelligence that might someday find them drifting between the stars. The crossing of the heliopause was a quiet milestone, marked by no fanfare from the spacecraft themselves. They simply continued their patient journey outward, their instruments noting the change in particle counts and magnetic field orientations. Yet it represented something profound. Humanity had reached beyond the sun's protective embrace into the true darkness between stars. Brown dwarfs occupy a twilight zone between planets and stars, too massive to be planets, but not massive enough to sustain the hydrogen fusion that powers true stars. They form like stars, from collapsing clouds of gas and dust, but they never achieve the core temperatures and pressures needed to ignite sustained nuclear reactions. Instead, they glow faintly from the residual heat of their formation, slowly cooling over billions of years. The boundary between a brown dwarf and a planet is somewhat arbitrary, usually set at about 13 times the mass of Jupiter, the threshold above which an object can briefly fuse deuterium, a heavy form of hydrogen. Below this mass, we call them planets. Above it, brown dwarfs. But the distinction is blurry, and some objects straddle the boundary, their classifications debated among astronomers. Brown dwarfs are dim and hard to find. Their glow mostly in infrared wavelengths invisible to our eyes. They fade as they age, the hottest ones shining a dull red, the oldest and coldest barely distinguishable from the background darkness of space. Some ancient brown dwarfs may have cooled so much that they are nearly invisible, their surfaces approaching room temperature, lukewarm objects drifting invisibly through the galaxy. These failed stars are surprisingly common, perhaps as numerous as true stars. They fill the space between stellar classes, a population of objects that almost became suns but fell just short in their slow fade toward darkness. They offer a glimpse of what happens when the universe's stellar machinery produces something slightly too small to shine. The universe at its largest scales is organized into structures of almost incomprehensible size. Galaxies cluster together into groups. Groups gather into clusters. Clusters combine into superclusters. And superclusters align along vast filaments that stretch for hundreds of millions of light years. These galactic filaments are among the largest coherent structures known to exist, chains of matter threading through the cosmos like the strands of an impossibly large web. The filaments are not random. They trace patterns laid down in the early universe, amplified over billions of years by gravity. The tiny density fluctuations in the cosmic microwave background, those minuscule variations in the temperature of the early universe, grew into the seeds of all large-scale structure. Where matter was slightly denser, it pulled in more matter, eventually forming galaxies, clusters, and the filaments that connect them. Between the filaments lie cosmic voids, enormous regions of space almost entirely empty of galaxies. Some of these voids span hundreds of millions of light years, their interiors containing perhaps only a handful of galaxies, where thousands might be expected. They are the negative space of the cosmic web, the emptiness that defines the structure by its absence. This architecture suggests deep principles at work, rules of organization that govern the distribution of matter across the largest scales. The cosmic web emerged not from chaos, but from physics, from gravity, from the initial conditions of the universe, from the interplay of dark matter and ordinary matter over billions of years. It is a reminder that even the seemingly random scatter of galaxies follows patterns we are only beginning to understand. Some white dwarfs, those dense remnants of sun-like stars, possess atmospheres composed almost entirely of carbon and oxygen. Under the extreme pressures at their surfaces, this carbon can crystallize into structures we would recognize as diamond. These stellar corpses are developing diamond atmospheres, layers of crystallized carbon forming as the stars slowly cool over billions of years, their exteriors gradually solidifying into something precious beyond measure. This crystallization process releases energy, actually slowing the cooling of the white dwarf as latent heat is released during the phase transition from liquid to solid. Astronomers have detected this effect by observing white dwarfs that appear slightly warmer than their ages would predict, evidence that crystallization is occurring in their interiors, releasing heat that prolongs their visible lifetimes. The largest white dwarfs may develop diamond cores the size of Earth, surrounded by progressively less dense layers of crystallized and gaseous material. These cosmic jewels will never be mined, never be admired in any conventional sense. They drift through the darkness, slowly transforming into the universe's most extravagant treasures, visible only to instruments that can detect their fading warmth. In the far future, when white dwarfs have cooled completely into black dwarfs, a process that takes longer than the current age of the universe, they may become solid spheres of crystallized carbon and oxygen, dark diamonds the size of planets, drifting eternally through a cold and empty cosmos. Beauty, it seems, can persist even when no one is left to witness it. Quasars are the most luminous, sustained objects in the cosmos, so bright that a single quasar can outshine the combined light of every star in its host galaxy. They are powered by supermassive black holes actively consuming matter, the infalling material heated to temperatures that produce radiation across the entire electromagnetic spectrum. At their peak, they can emit as much energy as trillions of suns, visible across billions of light years. When quasars were first discovered in the 1960s, astronomers were puzzled by their star-like appearance combined with their enormous redshifts, which indicated they were incredibly distant. The name quasar comes from quasi-stellar radio source. They looked like stars, but clearly were not. It took years to understand that these brilliant points of light were the active nuclei of distant galaxies, their central black holes gorging on matter and blazing with unimaginable energy. Most quasars existed in the early universe, when galaxies were younger and more gas-rich, providing abundant fuel for their central black holes. As galaxies aged and their gas was consumed or expelled, quasar activity declined. The universe today is far quieter than it was billions of years ago, its supermassive black holes mostly dormant, their feasting days behind them. When you look at a quasar, you are seeing light that has traveled for billions of years, emitted when the universe was young and violent. These beacons illuminate the cosmic past, allowing us to study conditions that no longer exist, epochs when black holes burned bright enough to outshine everything around them. Our galaxy, along with thousands of others in our cosmic neighborhood, is being pulled toward a region of space we call the Great Attractor. This gravitational anomaly lies about 250 million light-years away in the direction of the constellation Centaurus, and it is drawing galaxies toward it at roughly 600 kilometers per second. Yet despite its enormous influence, we cannot see it directly. It lies behind the dense star fields and dust clouds of the Milky Way's disk, hidden in a zone of avoidance that blocks our view. For decades, the Great Attractor was a mystery. We could measure its gravitational pull on surrounding galaxies, but we couldn't observe what was causing it. Only with infrared and X-ray telescopes capable of penetrating the obscuring dust have we begun to understand what lies there. The Great Attractor appears to be associated with a massive concentration of galaxies called the Norma Cluster, part of an even larger structure called the Laniakea Supercluster. But the mystery deepens further. Even the Great Attractor itself appears to be falling towards something larger, a region called the Shapley Supercluster, an even more massive concentration of galaxies that may be the true gravitational center pulling everything in our corner of the universe. We are caught in a cosmic flow, drawn by structures so vast they dwarf our imagination. The universe, it seems, has hierarchies of attraction. Just as the moon is drawn to Earth and Earth to the sun, and the sun to the galactic center, so too is our galaxy drawn toward ever larger structures, participating in flows and falls that span hundreds of millions of light years. Among the small worlds beyond Neptune, there is one shaped like an egg. Haumea is a dwarf planet so elongated that its longest axis is nearly twice the length of its shortest. This strange shape results from its incredibly rapid rotation. Haumea completes one full spin in just under 4 hours, faster than almost any other large body in the solar system. The centrifugal force of this rotation has stretched it into an ellipsoid, a cosmic egg tumbling through the outer darkness. Haumea's rapid spin is thought to result from a catastrophic collision early in its history, an impact so violent it not only set the dwarf planet rotating at tremendous speed, but also ejected debris that formed at least 2 small moons, Hikiaka and Namaka, and possibly contributed to a family of smaller icy bodies that share similar orbits. The violence of that ancient impact is written into Haumea's shape, preserved for billions of years in the cold reaches of the Kuiper Belt. Even more remarkably, Haumea possesses a ring, making it one of the few known dwarf planets with this feature. The ring was discovered in 2017 during observations of a stellar occultation, when Haumea passed in front of a distant star and the ring briefly dimmed the starlight. This ring is thin and dark, easily missed, but its presence adds another layer of complexity to this already unusual world. Haumea reminds us that even in the cold outer reaches of the solar system, where nothing much seems to happen, worlds can be strange and dynamic. Their histories written in shapes that defy our expectations of what a planet should look like. The largest known star in the universe, at least as of our current measurements, is Stephenson 2-18, a red supergiant located about 19,000 light-years from Earth. If placed at the center of our solar system, its surface would extend beyond the orbit of Saturn, engulfing Mercury, Venus, Earth, Mars, Jupiter, and Saturn within its bloated outer layers. It is roughly 2,150 times wider than our Sun, a sphere so vast that light would take hours to travel from one side to the other. And yet, despite this enormous size, Stephenson 2-18 is only about 30 to 40 times more massive than the Sun. The math seems impossible until you realize that red supergiants are extraordinarily diffuse. Their outer layers are so tenuous that they barely qualify as matter by earthly standards. The density at the star's surface is less than the density of air on a mountaintop. It is less a solid object than a vast, glowing suggestion of a star, a wisp of luminous gas spread across a volume we cannot easily comprehend. Stars like Stephenson 2-18 are nearing the end of their lives. They have exhausted the hydrogen in their cores and begun fusing heavier elements, their outer layers expanding as their internal structures change. Within a few million years, a cosmic eye blink, Stephenson 2-18 will likely explode as a supernova, collapsing down to a neutron star or black hole, while its outer layers are blasted into space. For now, it drifts through the galaxy, the largest star we know, a monument to what stellar physics allows when gravity and nuclear fusion conspire to create something almost too big to exist. In 2007, astronomers discovered something they had never seen before. A brief, intense burst of radio waves lasting only a few milliseconds, but carrying the energy of hundreds of millions of suns. This fast radio burst, as such events came to be known, arrived from far outside our galaxy, its origin a complete mystery. More detections followed, each one raising more questions than it answered. Something out there was producing these extraordinary flashes, and no one knew what. For years, the nature of fast radio bursts remained one of astronomy's most intriguing puzzles. Some bursts appeared only once, never repeating from the same location. Others repeated at irregular intervals, suggesting a source that persisted rather than being destroyed in a single cataclysmic event. Theories multiplied: colliding neutron stars, hyperactive magnetars, exotic physics we hadn't yet imagined. Someone even half-jokingly suggested alien transmissions. The mystery began to unravel in 2220, when a fast radio burst was detected from within our own galaxy, traced to a known magnetar, a neutron star with an extremely powerful magnetic field. The flash coincided with an X-ray burst from the same object, strongly suggesting that at least some fast radio bursts are produced by magnetars experiencing violent magnetic readjustments. The case was not closed entirely, but a major piece of the puzzle had fallen into place. Fast radio bursts offer a new way to probe the universe, their signals carrying information about the matter they pass through on their journey to Earth. Even as we unravel their origins, they continue to teach us about the space between galaxies, the distribution of matter in the cosmos, and the extreme physics of dying stars. Something is pushing the universe apart, and we don't know what it is. In 1998, astronomers discovered that the expansion of the universe is not slowing down, as gravity should cause it to, but accelerating. Distant galaxies are receding from us faster and faster, as if some invisible force is counteracting gravity on the largest scales. We call this force dark energy, a name that reflects our ignorance more than our understanding. Dark energy comprises approximately 68% of the total energy content of the universe. More than matter, more than radiation, more than anything else we can measure. Yet its nature remains almost entirely unknown. It may be a property of space itself, an intrinsic energy that empty vacuum possesses simply by existing. It may be a dynamic field that evolves over time. It may be something even stranger, something that requires new physics to explain. The discovery of dark energy was deeply unsettling to cosmologists. For decades, the main question had been whether the universe would expand forever or eventually collapse back on itself. The answer seemed to depend on how much matter the universe contained. No one expected the expansion to be accelerating, pushed outward by an unknown energy that dominates the cosmos. Whatever dark energy is, it is shaping the ultimate fate of the universe. If the acceleration continues indefinitely, galaxies will eventually be carried beyond each other's cosmic horizons, leaving each one isolated in an ever-emptying void. The universe may end not in fire or ice, but in loneliness, each galaxy a solitary island in infinite darkness, the gold in a wedding ring, the platinum in a catalytic converter, the uranium in nuclear reactors. All of these heavy elements were forged not in ordinary stars, but in the cataclysmic collisions of neutron stars. When these ultra-dense stellar remnants spiral together and merge, they create conditions of temperature and density so extreme that atomic nuclei are rapidly bombarded with neutrons, building up heavy elements through a process called rapid neutron capture. For decades, scientists suspected that neutron star mergers were responsible for many of the heaviest elements in the periodic table. But direct evidence was lacking. Then, in August 2017, the LIGO and Virgo gravitational wave detectors registered the signal of two neutron stars merging 130 million light-years away. Telescopes around the world turned to observe the aftermath, detecting a kilonova, a glowing cloud of newly formed heavy elements expanding outward from the collision site. The observations confirmed what theory had predicted. The kilonova's light signature matched models of freshly synthesized heavy elements, including gold, platinum, and uranium. A single neutron star merger can produce several Earth masses worth of gold, scattered into space to eventually be incorporated into new stars, planets, and perhaps even jewelry. Every gold atom you have ever touched was forged in the collision of neutron stars, events so violent they shake the fabric of space-time, so rare they occur only a few times per galaxy per million years. The precious metal in your life carries the memory of cataclysms that occurred billions of years ago, relics of the universe's most extreme alchemy, filling all of space, passing through you at this very moment, are neutrinos left over from the Big Bang. These cosmic neutrino background particles were released just 1 second after the universe began, when temperatures dropped enough for neutrinos to stop interacting with other matter. They have been drifting through space ever since, cooling as the universe expanded. Their energy is now so low they are virtually undetectable. About 300 cosmic background neutrinos pass through every cubic centimeter of space, including the space occupied by your body, at any given moment. They carry no charge, interact almost not at all with ordinary matter, and have masses so small we have only recently confirmed they have any mass at all. They are ghosts, relics of the universe's first seconds, older than atoms, older than light. We have never directly detected these primordial neutrinos. Their energies are far too low for current detectors, which rely on the rare interactions neutrinos have with other particles. Detecting the cosmic neutrino background would require technology far beyond what we currently possess. Instruments sensitive enough to catch particles that have been cooling for nearly 14 billion years. Yet we know they are there. The mathematics of the early universe demands their existence, and their gravitational effects are subtly imprinted on the cosmic microwave background and the large-scale structure of the universe. They are messengers from a time before light, witnesses to the universe's first moments, passing through us constantly without our awareness. We have discovered thousands of planets orbiting other stars, but finding moons around those planets, exomoons, has proven extraordinarily difficult. The same techniques that reveal exoplanets struggle with the smaller, fainter signals of moons. A planet passing in front of its star creates a detectable dip in brightness, but a moon's contribution to that dip is often too subtle to distinguish from noise or from variations in the planet's own signal. Scientists have announced several exomoon candidates over the years, but none have been conclusively confirmed. The most promising candidate, a possible Neptune-sized moon orbiting a Jupiter-sized planet called Kepler 1625b, remains debated. The signal is there in the data, tantalizing and suggestive, but alternate explanations cannot be ruled out. The first confirmed exomoon remains elusive, hovering just beyond the reach of our current instruments. This is frustrating because moons are expected to be common. Our own solar system has over 200 known moons, and the processes that form them should operate around other planets as well. Some of these moons might even be habitable. Large moons around gas giants in the habitable zone could have atmospheres, liquid water, and conditions suitable for life. The hunt for exomoons continues with new telescopes and improved techniques. Finding them would add an entirely new dimension to our understanding of planetary systems, revealing the satellites that accompany distant worlds, and perhaps identifying new environments where life might take hold. There is something curious about the fundamental constants of nature: the strength of gravity, the mass of the electron, the charge of the proton, and dozens of other values that define how physics works. If many of these constants were even slightly different, the universe as we know it could not exist. Stars might not form, or they might burn out too quickly. Atoms might not be stable. Chemistry might be impossible. Life, at least as we understand it, would have no chance to emerge. This observation is sometimes called the anthropic principle, and it comes in various strengths. The weak version simply notes that we can only observe a universe compatible with our existence. We couldn't find ourselves in a universe where observers were impossible. The strong version suggests something deeper might be at work, that the constants are somehow selected or designed to permit life. Neither version is fully satisfying, and the debate continues among physicists and philosophers. Some scientists propose that our universe is one of many, each with different fundamental constants, and we simply find ourselves in one compatible with observers because we couldn't exist in the others. This multiverse hypothesis is elegant but untestable. Those other universes, if they exist, are beyond our reach. Others suggest deeper principles we haven't yet discovered that constrain the constants to take the values they do. The fine-tuning puzzle remains unsolved, a question that sits at the intersection of physics, cosmology, and philosophy. Why is the universe the way it is? We don't know. But as you lie here, breathing and thinking and existing, you are living proof that somehow, against what seem like enormous odds, the constants aligned just right. Black holes, those objects from which nothing can escape, are not quite eternal. Through a process discovered theoretically by Stephen Hawking in 1974, black holes slowly radiate energy and lose mass over time. This Hawking radiation is extraordinarily faint, far too weak to detect with current instruments, but its implications are profound. Given enough time, every black hole will eventually evaporate completely, vanishing in a final burst of radiation. The mechanism involves quantum effects near the event horizon, where pairs of virtual particles pop into existence from the vacuum. Normally, these pairs would annihilate each other almost immediately, but near a black hole, one particle can fall in while the other escapes. The escaping particle carries away energy, and since energy and mass are equivalent, the black hole gradually loses mass. The process is almost unimaginably slow for large black holes, but accelerates as the black hole shrinks. A black hole with the mass of our Sun would take approximately 1067 years to evaporate, a 1 followed by 67 zeros. For comparison, the universe is currently about 1010 years old. Supermassive black holes would last even longer, perhaps 1,000 years or more. These time scales are so vast, they make the current age of the universe seem like the blink of an eye. In the far, far future, when all the stars have died and all the galaxies have faded, black holes will be among the last objects remaining, and even they will eventually disappear, leaving behind only radiation and the cooling void. Nothing lasts forever, not even the inescapable. One of the strangest ideas in modern physics is the holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary surface. Imagine everything in a room, every atom, every photon, every bit of data needed to describe the complete state of the room, being represented on the walls rather than within the space itself. The three-dimensional interior would be, in a sense, a projection of the two-dimensional boundary. This idea emerged from studies of black holes, where physicists discovered that the maximum information a region of space can contain is proportional not to its volume, but to its surface area. This was surprising. Intuitively, you would expect more space to hold more information. But black hole physics suggested otherwise, hinting at a profound connection between geometry and information. The holographic principle has been developed most rigorously in a theoretical framework called AD-S-CFT correspondence, which relates gravitational theories in certain curved spaces to non-gravitational theories on their boundaries. While this doesn't directly apply to our universe, it has proven remarkably powerful as a tool for understanding quantum gravity and the nature of space-time. If something like the holographic principle applies to our universe, it would mean that our three-dimensional experience might be a kind of projection from a two-dimensional reality we cannot perceive directly. It's a deeply counterintuitive idea, one that challenges our basic assumptions about the nature of space and existence. Yet the mathematics keeps pointing in this direction, suggesting that reality may be far stranger than our everyday experience suggests. Every atom in your body heavier than hydrogen was forged in the heart of a star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was created through nuclear fusion in stellar cores, or in the explosive deaths of massive stars. You are, quite literally, made of stardust, assembled from elements scattered across space by stars that died billions of years before you were born. The process works like this. Stars burn hydrogen into helium, then helium into carbon and oxygen. Massive stars continue the process, building up heavier elements, layer by layer in their cores: neon, magnesium, silicon, and finally iron. Iron is the end of the line for fusion. Creating heavier elements requires more energy than it releases. When a massive star's core becomes iron, it collapses, and the star explodes as a supernova, blasting its accumulated elements into space. Even heavier elements, gold, platinum, uranium, require the extreme conditions of neutron star mergers or supernovae to form. These elements are rarer because the events that create them are rarer, but they too end up scattered through interstellar space, mixing with gas clouds that will eventually collapse to form new stars and planets. The star that contributed the calcium in your teeth may not be the same star that provided the iron in your hemoglobin. You are a mosaic assembled from many sources, many stellar deaths, many scattered clouds of enriched gas. The universe has been preparing the ingredients for you for nearly 14 billion years, and here you are, briefly animate, contemplating your origins before sleep. The cosmic microwave background radiation, that ancient light from 380,000 years after the Big Bang, is not perfectly uniform. It contains tiny temperature fluctuations, variations of about 1 part in 100,000, representing slight differences in density in the early universe. These minuscule fluctuations were the seeds from which all structure in the universe eventually grew. Where the early universe was slightly denser, gravity pulled in more matter, amplifying the density differences over time. Over hundreds of millions of years, these slightly denser regions collapsed into the first stars and galaxies. The pattern of fluctuations in the cosmic microwave background is directly connected to the distribution of galaxies we see today, The seeds became the cosmic web. These fluctuations originated even earlier, during cosmic inflation, a period of extremely rapid expansion in the universe's first fraction of a second. Quantum mechanical fluctuations, normally confined to the subatomic scale, were stretched to cosmic sizes during inflation, imprinting themselves on the fabric of the universe. The largest structures in the cosmos trace their origins to quantum randomness, magnified beyond comprehension. When scientists map the cosmic microwave background with satellites like COVI, WMAP, and Planck, they are photographing the seeds of everything. Every galaxy, every star, every planet, every person, all of it began as slight variations in the temperature of light released when the universe was less than 500,000 years old. You are descended, in a very real sense, from a quantum fluctuation. The Big Bang was not an explosion in space, but an expansion of space itself, and with it, an expansion of time. According to our best understanding of cosmology, time as we know it began with the Big Bang. There was no before, because time itself didn't exist before the universe began. Asking what happened before the Big Bang may be as meaningless as asking what lies north of the North Pole. The question contains a hidden assumption that doesn't apply. This is one of the most difficult concepts to grasp about the origin of the universe. We are accustomed to thinking of time as a backdrop against which events unfold, an infinite stage stretching eternally into the past and future. But general relativity tells us that time is part of the fabric of space-time, woven together with the three dimensions of space. If space-time had a beginning, then time had a beginning. Some cosmological models propose that the Big Bang was not the absolute beginning, but a transition from some prior state, a bouncing universe that contracted before expanding, or a bubble nucleating in a larger multiverse. These ideas are speculative and difficult to test, but they suggest that the question of ultimate origins remains open. Perhaps our universe is one chapter in a larger story we cannot yet read. What we can say with confidence is that the universe we observe has a finite age, that space-time as we know it began approximately 13.8 billion years ago, and that our concepts of time and causation may not extend beyond that boundary. The beginning, if there was one, lies beyond the reach of our current understanding. The observable universe is not the entire universe, but merely the portion from which light has had time to reach us since the Big Bang. This cosmic horizon lies about 46 billion light years away in every direction, a distance that seems to contradict the universe's age of 13.8 billion years, until you account for the expansion of space that has carried distant objects even farther away since their light began traveling toward us. Beyond this horizon, the universe almost certainly continues. There is no edge, no wall, no boundary where existence stops. The observable universe is simply the bubble within which we can receive information. Light from regions beyond has not yet had time to arrive, and because the universe is expanding faster than the speed of light at sufficient distances, some of that light will never arrive. Those regions are beyond our cosmic horizon, forever inaccessible. The full extent of the universe may be infinite, an endless expanse of galaxies stretching forever in every direction. Or it may be finite, but unbounded, curved back on itself like the surface of a sphere. so that traveling far enough in one direction would eventually bring you back to your starting point. We don't know, and we may never know. The information we need lies beyond the horizon we can observe. The observable universe contains something like 2 trillion galaxies, each with billions of stars, spread across 93 billion light years of diameter. And yet, this may be only an infinitesimal fraction of what exists. We are limited to our bubble, our window, our small view of something that may be incomprehensibly larger. Some theories in physics suggest that our universe may be just one of an infinite number of universes, each with its own laws of physics, its own constants of nature, its own history. This multiverse hypothesis arises from several independent lines of reasoning. Eternal inflation, the many worlds interpretation of quantum mechanics, string theory's landscape of possible vacua. Each suggests in its own way that what we call the universe may be only a small part of a much larger reality. In eternal inflation, the rapid expansion that occurred in our universe's first moments continues forever in some regions, spawning new universes as bubbles in an ever-inflating foam. Each bubble would be a universe unto itself, potentially with different physical properties. Our universe would be one such bubble, isolated from its siblings by expanding space that prevents any communication between them. The multiverse is a controversial idea because it may be inherently untestable. If other universes exist beyond any possible observation, how can we ever verify their existence? Some argue this makes the multiverse unscientific, a matter of philosophy rather than physics. Others contend that if well-established theories predict the multiverse, we should take the prediction seriously, even if direct confirmation is impossible. Whether or not the multiverse exists, the idea forces us to confront deep questions about the nature of existence and our place within it. Are we unique, or are we one version of ourselves among infinite variations? The answers, if they exist, may lie forever beyond our reach. The geometry of the universe appears to be flat. This doesn't mean the universe is two-dimensional, but rather that on cosmic scales, the rules of Euclidean geometry apply. Parallel lines remain parallel forever. The angles of a triangle sum to exactly 180 degrees. Light travels in straight lines unless deflected by mass. Space does not curve back on itself or bend away into negative curvature. This flatness is extremely precise. Measurements from the cosmic microwave background show that the universe is flat to within about 0.4%. This is remarkable because flatness is an unstable condition in cosmology. A universe that was even slightly curved at the beginning would have become more curved over time, either collapsing back on itself if positively curved or expanding into hyperbolic geometry if negatively curved. The fact that it remains almost perfectly flat after 13.8 billion years requires explanation. The leading explanation is cosmic inflation, that brief period of exponential expansion in the universe's first fraction of a second. Inflation would have stretched any initial curvature to effectively zero. Just as the surface of a balloon appears flat when inflated to enormous size. If inflation occurred, flatness is a natural outcome, not a cosmic coincidence. The flatness of the universe has implications for its fate. A flat universe will expand forever, never collapsing, never closing back on itself. It suggests an infinite extent, an endless cosmos, stretching beyond our observable bubble. The geometry of space itself points toward eternity. In the first tiny fraction of a second after the Big Bang, somewhere around 10 hours 36 seconds, the universe may have undergone a period of exponential expansion called cosmic inflation. During this brief epoch, the universe expanded by a factor of at least 10^26, perhaps much more. Regions that were once in causal contact, able to exchange information and reach equilibrium, were suddenly stretched to cosmic distances, far beyond each other's horizons. Inflation solves several puzzles about the universe. It explains why the cosmic microwave background is so uniform. Distant regions look similar because they were once close enough to equilibrate before inflation separated them. It explains the flatness of space. Any initial curvature was stretched to effectively zero. And it explains the origin of the density fluctuations that seeded all structure. Quantum fluctuations were amplified to cosmic scales during the inflationary expansion. The cause of inflation remains unknown. Cosmologists postulate a field called the inflaton that drove the expansion, but its properties and connection to other physics are poorly understood. Inflation ended when this field decayed, releasing its energy as the hot, dense plasma that became the early universe we observe in the cosmic microwave background. Inflation pushed the scale of human imagination to its limits. In a time span too brief to comprehend, the universe expanded by a factor too large to visualize, setting the stage for everything that followed. All the structure we see, all the galaxies and stars and planets, can trace their origins to this primordial stretching of space-time. The universe should not contain any matter at all. According to our best theories of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy. If the universe had been perfectly symmetric, every particle would have found its antiparticle partner, and the cosmos would contain nothing but radiation. No atoms, no stars, no planets, no people. Yet here we are, surrounded by matter. Somehow, in the first moments after the Big Bang, a slight asymmetry emerged. For every billion pairs of matter and antimatter particles that annihilated, roughly one extra matter particle survived. This tiny imbalance, about 1 part in a billion, was enough. When the annihilation was complete, that small residue of matter was all that remained, and from it, everything we know was built. The origin of this asymmetry remains one of the deepest mysteries in physics. We know it happened. We don't know how. Particle physics experiments search for processes that treat matter and antimatter differently, hoping to find clues. Theories propose mechanisms involving exotic particles and conditions that existed only in the first instance after the Big Bang. But no explanation has been confirmed. Your existence depends on this unexplained asymmetry. Every atom in your body, every star you see, every galaxy in the observable universe, all of it exists because of a slight imbalance we cannot yet account for. The universe played favorites, and you are the beneficiary of its inexplicable preference. When physicists calculate the energy that empty space should contain, the so-called vacuum energy, they arrive at a number so large it seems absurd. Quantum field theory predicts that the vacuum is not truly empty, but seeds with virtual particles popping in and out of existence. The energy associated with these fluctuations should be enormous, contributing a cosmological constant that would have torn the universe apart almost immediately after the Big Bang. But when we measure the actual energy density of empty space, the dark energy driving the universe's accelerating expansion, we find a value roughly 120 orders of magnitude smaller than the prediction, a factor of 10^120. This is the largest discrepancy between theory and observation in the history of physics, sometimes called the worst prediction ever made. Something is catastrophically wrong, either with our understanding of quantum field theory or with how gravity responds to vacuum energy. Perhaps some unknown mechanism cancels most of the vacuum energy, leaving only the tiny residue we observe. Perhaps the calculation itself is flawed in ways we don't understand. Physicists have struggled with this problem for decades without resolution. The cosmological constant problem is humbling. It reveals the limits of our understanding, the places where our theories fail spectacularly. We can describe so much of the universe with remarkable precision, yet this one calculation goes wrong by a factor larger than any number you will ever encounter in daily life. We do not know how the universe will end. Several fates are possible, depending on properties of dark energy that remain uncertain. If dark energy remains constant, the universe will expand forever, galaxies drifting apart until each is isolated in an ever-emptying void. Stars will burn out, black holes will evaporate, and the cosmos will fade into a cold, dark equilibrium called heat death. But if dark energy increases in strength over time, a more dramatic fate awaits. In a scenario called the Big Rip, the accelerating expansion eventually tears apart galaxies, then solar systems, then planets, then atoms themselves. Space-time would be stretched until nothing remains connected to anything else, until the fabric of reality is shredded by its own expansion. Other possibilities exist as well. Perhaps the dark energy field is unstable and will one day decay, triggering a phase transition that remakes the universe entirely. Perhaps we live in a false vacuum, and a bubble of true vacuum could nucleate somewhere, expanding at the speed of light and rewriting physics as it goes. These scenarios are speculative, but they remind us that the future is not guaranteed. The end, whatever form it takes, lies unimaginably far in the future, trillions or googles of years from now. For tonight, the universe remains young and full, and you can rest in the knowledge that whatever ending awaits, it is not coming soon. There is a deep and unresolved mystery at the heart of quantum mechanics, the role of observation and measurement in determining physical reality. In the standard interpretation, quantum systems exist in superpositions of multiple states until they are measured, at which point they collapse into a single definite outcome. But what constitutes a measurement? What causes the collapse? Some have speculated that consciousness itself might play a fundamental role. This idea remains highly controversial among physicists. Most prefer interpretations that don't require invoking consciousness. The wave function might collapse due to interactions with the environment, or perhaps it never collapses at all, with all outcomes existing in parallel branches of reality. Consciousness, in these views, is a phenomenon that emerges from physical processes, not a fundamental ingredient in the laws of physics. Yet the question lingers: why does the universe appear determinate to conscious observers? Why do we experience a single, definite reality rather than the smeared probabilities of quantum mechanics? These questions touch the boundaries of physics and philosophy, where hard science meets the deepest puzzles of existence. Perhaps consciousness is simply what information feels like when processed in certain ways. Perhaps it is an emergent property of complex systems, no more mysterious than wetness emerging from water molecules. Or perhaps, in ways we don't yet understand, mind and matter are more intimately connected than our current theories suggest. Given the vast number of stars in our galaxy, the billions of potentially habitable planets, and the billions of years available for life to evolve and develop technology, we might expect the universe to be teeming with evidence of other civilizations. Radio signals, megastructures, probes visiting our solar system. Something should have revealed their presence by now. Yet we have found nothing. This puzzling silence is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Many explanations have been proposed. Perhaps life is far rarer than we assume, requiring conditions so specific that Earth may be unique. Perhaps intelligence is common, but technological civilizations are short-lived, destroying themselves before they can spread across the stars. Perhaps advanced civilizations deliberately hide, or exist in forms we cannot recognize, or have no interest in contacting primitive species like ourselves. Each explanation carries profound implications. If we are alone, the cosmos is lonelier than we imagined, but also perhaps more precious. Our small planet, the only harbor of consciousness in an unimaginably vast ocean. If civilizations routinely destroy themselves, we face a warning about our own future. If they are hiding or transcended, the universe may be far stranger than our science fiction suggests. The silence continues. Every search for extraterrestrial intelligence has returned empty. Perhaps tomorrow will bring detection, or perhaps we will search for centuries and find nothing. Either answer would transform our understanding of our place in the cosmos. We may be living in a particularly special era of the universe's history. Right now, the cosmos is old enough for stars to have formed and seeded space with heavy elements, but young enough that stars still shine abundantly. Galaxies are close enough to see. The cosmic microwave background is still detectable, and the expansion of the universe has not yet isolated every galaxy beyond the horizon of every other. In the far future, this will change. The accelerating expansion will carry distant galaxies beyond our observable universe. The cosmic microwave background will redshift into undetectable wavelengths. Future astronomers, if any exist, will see only their local galaxy cluster, the rest of the universe having faded from view. They may conclude they live in a static, isolated cosmos, with no evidence of the Big Bang, no distant galaxies to observe, no way to deduce the true nature of reality. We live in an epoch when the evidence is still visible, when the universe reveals its history to anyone who looks. This may be a brief window, long by human standards, but short by cosmic ones. In trillions of years, the clues will have vanished, the records erased, the story of the universe's origin lost to observers who come too late. Perhaps this is why we find ourselves here now, contemplating these questions, because now is when the contemplation is possible, when the evidence persists, when the universe still remembers its own beginning. The universe's most likely fate is not dramatic annihilation, but slow fade into equilibrium. In a scenario called heat death, the cosmos gradually approaches maximum entropy, a state where energy is evenly distributed and no useful work can be extracted from any system. Stars burn out, black holes evaporate, even protons may eventually decay. What remains is a thin soup of particles at nearly uniform temperature, drifting through an ever-expanding void. This process unfolds over timescales that dwarf the current age of the universe. Stars will continue forming for trillions of years. The last red dwarfs will burn for tens of trillions of years more. Black holes will take 1067 to 10100 years to evaporate. The final approach to equilibrium may require 10120 years, a number so large that writing it out would be meaningless. Heat death is not a catastrophic ending, but a gradual winding down, a slow relaxation into the lowest energy state. The universe doesn't end so much as it stops happening. All processes cease because there are no longer any energy gradients to drive them. Time itself may become meaningless in such a state, with nothing to mark its passage. This vision of the future is melancholy, but also strangely peaceful. The universe, having burned bright with stars and galaxies and perhaps life, will eventually rest. The long story will end not with a bang, but with a whisper, fading into silence. After centuries of scientific investigation, after the development of telescopes and particle accelerators and gravitational wave detectors, after mapping the cosmic microwave background and cataloging billions of galaxies, we have determined the composition of the universe. Ordinary matter, the atoms that make up stars, planets, and people, comprises only about 5% of the total. The rest is dark matter and dark energy, substances we cannot see, cannot touch, and do not understand. Dark matter accounts for roughly 27%, its presence inferred from gravitational effects on galaxies and light. Dark energy makes up about 68%, detected through the accelerating expansion of the universe. Together, these unknown components dominate the cosmos, shaping its structure and fate, while the familiar matter of our experience is a minor ingredient. This is a humbling realization. We have built elaborate theories to describe the behavior of matter and energy, confirmed by countless experiments and observations. Yet most of the universe lies outside these theories, operating according to rules we haven't deciphered. Our physics describes the exception, not the rule. The universe remains largely mysterious, and the greatest discoveries may lie ahead. Perhaps the nature of dark matter and dark energy will be revealed in the coming decades, completing our picture of cosmic reality. Or perhaps the answers will prove elusive, forever hovering just beyond the reach of human understanding. Physicists have long sought a theory of everything, a single framework that would unite all the fundamental forces and particles into one coherent description of reality. Such a theory would explain why the universe is the way it is, why the constants have their particular values, why gravity and quantum mechanics seem to follow incompatible rules. It would be the ultimate achievement of human understanding, the complete story of existence. String theory is one candidate, proposing that the fundamental entities are not point particles, but tiny vibrating strings whose different modes of vibration correspond to different particles. Loop quantum gravity is another approach, attempting to quantize space-time itself. Other theories explore extra dimensions, emergent space-time, and mathematical structures beyond our current imagination. None of these candidates has been confirmed. String theory remains untested, its predictions difficult to verify with current technology. Loop quantum gravity makes different predictions that are equally challenging to observe. The theory of everything, if it exists, remains undiscovered, a grail sought by generations of physicists who sense its existence without being able to grasp it. Perhaps such a theory is possible, waiting to be found. Perhaps the universe is fundamentally comprehensible, its laws reducible to a single elegant principle. Or perhaps complexity goes all the way down and no final theory exists. Either possibility is profound, speaking to the nature of reality and the limits of human reason. For as long as humans have existed, we have looked at the night sky and wondered. Cave painters depicted stars alongside hunting scenes. Ancient astronomers tracked the movements of planets and predicted eclipses. Philosophers contemplated the nature of the cosmos and our place within it. The questions we ask today about the origin of the universe, the nature of space and time, the possibility of life elsewhere, are the same questions our ancestors asked, refined and expanded, but fundamentally unchanged. This tradition connects us across millennia. The same stars that guided Polynesian navigators across the Pacific shine on you tonight. The same moon that inspired ancient poets casts its light through your window. The same sense of wonder that moved anonymous stargazers thousands of years ago stirs in you now, as you contemplate the vastness above your roof. Science has revealed truths our ancestors could not have imagined. The scale of the cosmos, the age of stars, the existence of galaxies beyond our own. But it has not diminished the wonder. If anything, the more we learn, the more astonishing the universe becomes. Each answer reveals new questions. Each discovery opens new mysteries, and the cosmos remains as inexhaustible as it was when the first human looked up and asked why. Tonight, you join that ancient tradition. You lie beneath the same sky that has canopied every human who ever lived, participating in a contemplation older than civilization. The stars do not care that you are watching, but you care, and that caring is itself a kind of miracle. Consciousness arising from stardust, turning its attention back to the stars from which it came. And so we come to the end of our journey together, at least for tonight. We have traveled far, from the subtle substance of supposedly empty space to the ancient light of the cosmic microwave background, from the slow patience of red dwarf stars to the violent brilliance of colliding neutron stars, from the frozen heart of Pluto to the hidden oceans of distant moons. We have contemplated the birth of time and glimpsed possible endings, wandered through structures larger than imagination, and paused to consider the quantum strangeness at the smallest scales. The universe we have seen is vast beyond comprehension, yet it is also our home. The same physics that governs the most distant quasar governs the atoms in your body. The same gravity that bends light around black holes holds you gently to your bed. You are not separate from the cosmos, but woven into it, made of its materials, shaped by its laws, participating in its ongoing story. Perhaps that thought can bring a kind of peace as sleep approaches. Whatever worries occupied your day, whatever concerns await tomorrow, you are also this, a temporary arrangement of ancient atoms, contemplating the universe that made you, resting beneath the same stars that have watched over every generation of dreamers who came before. The questions we explored tonight have no final answers, and perhaps that is as it should be. The mystery remains, inexhaustible and inviting, waiting for the next night you choose to wander through it. The stars will be there, patient as ever, keeping their silent vigil while you sleep. So let your eyes grow heavy now. Let your thoughts drift like galaxies through the darkness of your mind. The universe will continue its ancient dance while you rest. Stars burning, planets turning, light traveling across the void. And tomorrow, if you choose, you can look up again and remember that you are part of something so much larger than a single life, a single world, a single moment in time. Thank you for spending this time with me. Sleep well and dream of stars. Good night.